The James Webb Space Telescope was designed to extend human observation deeper into the universe than ever before, not by looking for dramatic events, but by resolving unanswered questions about how cosmic structures formed. Its primary strength lies in its ability to observe faint, distant objects from the early universe, with enough precision to test long-standing theoretical limits. In doing so, it has begun to expose gaps between what current models predict and what the universe appears to contain. This documentary examines one such gap, not a single image or isolated discovery, but a set of observations that challenge assumptions about black hole formation, early galactic development, and the distribution of unseen mass. The concern is not immediate danger, but implication. If the interpretations supported by JWST data are correct, they suggest that fundamental aspects of cosmic structure may have formed through mechanisms that were previously considered unlikely or even impossible. What scientists mean by terrifying in modern astronomy. In scientific contexts, the word terrifying does not describe fear in the emotional sense. It describes disruption. A discovery becomes unsettling when it undermines assumptions that many other ideas depend on. In astronomy and cosmology, this usually means observations that challenge how matter, energy, and structure are thought to behave across time. For most of the past century, cosmology has been built on a layered framework. The expansion of the universe, the formation of stars, the growth of galaxies, and the emergence of large-scale structure are all modeled as processes that follow from a small set of initial conditions. These models are not speculative. They are tested against observations repeatedly and refined when discrepancies appear. Stability in these models matters because many conclusions rely on them simultaneously. A finding becomes disturbing when it does not simply add a new object or phenomenon, but instead questions whether a foundational step in that framework is correct. In such cases, the concern is not that something dangerous has been found, but that the logical chain connecting early conditions to present-day structures may be incomplete. The James Webb Space Telescope has introduced this kind of disruption. Its observations do not show exotic events in isolation. Instead, they reveal ordinary-looking systems appearing at times when, according to current understanding, they should not yet exist. The tension lies in timing, scale, and abundance rather than appearance. In astronomy, timing is critical. Many processes have hard physical limits. Stars require time to form, evolve, and die. Heavy elements require multiple generations of stars. Black holes formed from stellar collapse cannot grow arbitrarily fast without violating radiation pressure constraints. When objects appear earlier than these limits allow, the models that explain their origin come into question. This is where the sense of unease arises. JWST has repeatedly observed massive black holes and mature galactic structures at epochs when the universe was only a few 100 million years old. These are not marginal cases. They are numerous enough to suggest that they are not rare anomalies. If the existing formation pathways cannot account for them, then either the pathways are incomplete or a different mechanism operated in the early universe. The discomfort is amplified because black holes are not isolated curiosities. They are deeply linked to galaxy formation, star formation regulation, and the distribution of matter. Changing how black holes form changes how galaxies assemble. Changing how galaxies assemble affects how matter clusters on the largest scales. A single unresolved inconsistency can propagate through the entire theoretical structure. The term terrifying is therefore shorthand for theoretical instability. It reflects the possibility that accepted explanations may require significant revision. In science, such moments are not unusual, but they are consequential. Past examples include the discovery of cosmic expansion, the realization that most matter is invisible, and the observation that the universe's expansion is accelerating. Importantly, this reaction is not driven by speculation alone. It emerges when observations are robust, repeatable, and difficult to reconcile with established theory. JWST's data meet these criteria. Its instruments have been calibrated extensively. Its observations are cross-checked with other facilities. The anomalies persist. Another reason these findings are unsettling is that they intersect multiple unresolved problems at once. Black hole formation, dark matter, early universe density fluctuations, and chemical evolution are often treated as separate topics. JWST observations increasingly suggest they may be connected more directly than previously thought. A solution proposed for one problem can influence all the others. This convergence raises the stakes. If early black holes formed through mechanisms not currently included in standard models, then the initial conditions of the universe may have been different in meaningful ways. That would affect how matter collapsed, how radiation interacted with structure, and how the first galaxies emerged. None of this implies immediate danger. The universe is not behaving unpredictably in a way that threatens present-day systems. The concern is intellectual rather than physical. It is about whether the universe followed the developmental path that cosmology has long assumed. In this sense, terrifying reflects the cost of being wrong at a fundamental level. Scientific theories are valuable because they compress complexity into coherent explanations. When those explanations begin to fail, the work required to rebuild them is substantial. The chapters that follow examine one possible source of this disruption, not as a claim, but as a line of inquiry driven by data. The goal is to understand why JWST observations have reopened questions that many researchers believed were already settled, and what it would mean if the universe did not evolve in the way current models describe. Why JWST changed the scale of what can be discovered. The James Webb Space Telescope represents a shift in observational capability rather than an incremental improvement. Earlier space telescopes extended vision deeper into space, but they remained constrained by wavelength, sensitivity, and resolution limits that shaped what questions could realistically be asked. JWST altered those constraints simultaneously, changing not only what can be seen, but how early cosmic history can be tested. The central difference lies in infrared observation. As the universe expands, light from distant objects is stretched to longer wavelengths. Galaxies that emitted visible or ultraviolet light billions of years ago now appear primarily in the infrared. Previous telescopes could detect only the brightest of these sources, often without sufficient detail to analyze their structure or composition. JWST was designed specifically to operate where this redshifted light now resides. Infrared sensitivity allows JWST to observe objects from epochs previously accessible only through indirect inference. This includes the period when the first stars ignited, when the earliest galaxies assembled, and when black holes began influencing their environments. Observations from this era were once limited to sparse detections and statistical trends. JWST provides resolved data instead. Resolution is equally critical. Detecting a faint object is not enough to understand it. Structure, motion, temperature, and chemical composition all require spatial and spectral clarity. JWST's segmented mirror, far larger than that of any prior space telescope, delivers this clarity at infrared wavelengths. Features that once blurred into unresolved points now appear as extended systems with measurable internal properties. This combination of depth and resolution alters how discoveries emerge. Earlier telescopes often revealed anomalies as outliers, objects that seemed unusual but could be dismissed as rare or extreme. JWST shows populations. It reveals not just one early massive galaxy or one unexpectedly large black hole, but many. Repetition transforms surprise into a pattern. Spectroscopy further expands the telescope's impact. JWST does not merely image distant objects. It decomposes their light to determine chemical content, temperature, ionization state, and motion. These measurements are essential for reconstructing evolutionary history. Metallicity, for example, provides a record of how many stellar generations have occurred. Low metallicity indicates youth. High metallicity implies prolonged star formation. This capability is crucial for evaluating formation timelines. a galaxy with a mature structure but primitive chemistry, challenges standard sequencing. Under conventional models, structure and enrichment advance together. JWST has identified systems where they do not. That discrepancy could not be established convincingly without precise infrared spectroscopy. JWST also observes through dust with minimal obstruction. Dust absorbs visible light and hides star-forming regions, galactic centers, and early accretion activity. Infrared wavelengths penetrate these regions, exposing processes previously inferred only indirectly. This has revealed active phenomena in places thought to be quiescent and has clarified the distribution of mass within early systems. Another change concerns scale. JWST surveys wide fields while retaining sensitivity to faint objects. This enables statistically meaningful samples rather than isolated detections. Patterns in early galaxy populations can be analyzed across environments, masses, and redshifts. Theoretical models can be tested against distributions rather than single cases. Importantly, JWST's discoveries are not limited to one domain. Findings related to early galaxies intersect with black hole research, chemical evolution, and large-scale structure formation. Observations in one area constrain interpretations in others. The telescope forces cross-disciplinary consistency. This interconnectedness magnifies the impact of discrepancies. When JWST observations conflict with expectations, the issue is rarely local. A mismatch in black hole mass affects galaxy assembly models. A mismatch in metallicity affects star formation history. A mismatch in abundance affects cosmological parameters. The telescope exposes these tensions simultaneously. JWST also reduces reliance on extrapolation. Previously, models of the early universe were constrained by present-day observations and theoretical assumptions. JWST provides direct evidence from the relevant epoch. This shifts uncertainty from observation to interpretation. The data exist. The challenge is explaining them. Another factor is reliability. JWST observations are repeatable and verifiable. Independent teams analyze the same data using different methods and reach similar conclusions. This reduces the likelihood that anomalies result from instrumentation or processing errors. Persistence across datasets strengthens their significance. The scale of discovery is therefore not measured solely in distance or age, but in consequence. JWST has compressed the gap between theory and observation. It has reduced the margin where assumptions could hide. Processes once treated as speculative now face empirical scrutiny. This does not mean that existing models are invalid. Many remain broadly successful, but JWST reveals that they may be incomplete in critical early phases. The universe appears capable of organizing mass faster, earlier, or through pathways not fully accounted for. That realization defines the telescope's significance. JWST did not simply find new objects. It altered which questions can be answered with evidence rather than conjecture. In doing so, it shifted the boundary between what cosmology explains and what it must now confront directly. The problem of black hole origins before JWST. Before the James Webb Space Telescope began returning data, the origin of black holes was considered one of the more constrained problems in astrophysics. The basic formation pathway appeared well understood. Black holes formed when massive stars exhausted their nuclear fuel, collapsed under their own gravity, and left behind compact remnants. These remnants, if sufficiently massive, became stellar black holes. Larger black holes were thought to arise through gradual growth over cosmic time. This framework worked well for nearby systems. Observations of stellar evolution, supernova remnants, and compact objects in the Milky Way supported it. Stellar black holes, with masses a few to tens of times that of the Sun, were detected through X-ray binaries and gravitational wave events. Their properties aligned with predictions from stellar collapse models. The difficulty emerged when attention shifted to supermassive black holes. By the late 20th century, it had become clear that nearly every large galaxy hosts a black hole at its center. with masses ranging from millions to billions of solar masses. These objects exert strong influence over their host galaxies, regulating star formation and shaping galactic structure. The accepted explanation was hierarchical growth. A small black hole seed forms from stellar collapse. Over billions of years, it gains mass by accreting gas and merging with other black holes. This process is limited by radiation pressure. As matter falls in, it heats up and emits energy. That energy pushes back against infalling material, placing an upper bound on how fast a black hole can grow. This growth limit is well defined. Under steady conditions, a black hole accreting at the maximum allowed rate requires hundreds of millions of years to increase its mass by an order of magnitude. Growing from a stellar remnant to a billion solar mass object therefore requires most of cosmic history. Within this framework, the existence of supermassive black holes in the present-day universe was not problematic. However, even before JWST, cracks were visible. Observations of distant quasars showed supermassive black holes existing less than a billion years after the Big Bang. These objects were already extremely massive at a time when the universe itself was young. While still theoretically possible, their existence strained growth models. To reconcile this, several extensions were proposed. Some models allowed periods of super-Eddington accretion, where black holes temporarily exceed standard growth limits. Others invoked unusually massive initial stars, capable of producing larger seed black holes. These ideas remained controversial, but were not ruled out by available data. Crucially, the evidence base was limited. Observations of early black holes relied on rare, extremely luminous quasars. These objects could represent exceptional cases rather than typical behavior. Without a large population sample, it was difficult to determine whether early supermassive black holes were common or anomalous. Another unresolved issue concerned environment. Black hole growth depends on the availability of gas. Early galaxies were thought to be small, chaotic, and inefficient at delivering gas to their centers. Sustained accretion at the required rates seemed difficult under these conditions, yet models lacked direct observational constraints on early galactic structure. Chemical evidence also posed questions. Heavy elements are produced by stars. Galaxies hosting massive black holes should show signs of multiple stellar generations. Some early systems, however, appeared chemically primitive, suggesting limited prior star formation. This was difficult to reconcile with black holes grown from stellar remnants. Despite these tensions, the prevailing view held that refinements within the existing framework would suffice. The fundamental sequence remained intact. Stars form first, black holes form from stars, and large black holes grow slowly over time. The lack of decisive contradictory evidence allowed this assumption to persist. What limited progress was not theoretical imagination, but observational reach. Telescopes before JWST could not reliably probe the earliest phases of galaxy formation. They detected endpoints, not origins. Black holes were seen when already massive, not during formation. As a result, models were built forward from assumptions rather than backward from data. The early universe remained a boundary condition rather than a testable regime. The possibility that black holes formed through entirely different mechanisms existed, but lacked empirical support. This was the state of the field when JWST launched. Black hole origins were considered challenging but tractable. Theoretical tension existed, but it was localized. Few anticipated that new observations would suggest not just faster growth, but fundamentally different starting points. JWST changed that by providing direct access to the era where these assumptions mattered most. Instead of inferring early conditions from mature systems, it allowed those conditions to be examined directly. The problem of black hole origins shifted from one of parameter adjustment to one of foundational validity. Understanding why that shift occurred requires examining what JWST actually saw and why those observations could not be easily absorbed into pre-existing models. the discovery of massive black holes in the early universe. When observations first indicated the presence of massive black holes in the early universe, the issue was not their existence alone, but their timing. Under established models, black holes require extended periods to grow. Finding them at early epochs meant that either growth occurred faster than allowed, or formation began from much larger starting masses. Before JWST, evidence for early massive black holes came primarily from quasars detected at high redshift. These objects were extraordinarily luminous, indicating accreting black holes with masses exceeding hundreds of millions of solar masses. While rare, they were unmistakable. Their redshifts placed them within the first billion years after the Big Bang. Initially, these detections were treated as exceptional. Quasars are the most extreme manifestations of black hole activity, and it was plausible that they represented statistical outliers. The broader population of early galaxies remained largely inaccessible, leaving uncertainty about whether such black holes were common or anomalous. JWST altered that picture by expanding the observable sample. It identified numerous early galaxies hosting energetic central sources consistent with massive black holes. These were not all quasars. Many were moderate in luminosity, embedded within galaxies that would previously have gone undetected. This suggested that early massive black holes were not isolated curiosities, but part of a broader population. The redshift range of these detections was critical. Some objects appeared at times when the universe was only a few 100 million years old. At such ages, even optimistic growth scenarios struggled to explain the inferred masses. The discrepancy was no longer confined to a handful of extreme cases. Mass estimates relied on multiple lines of evidence. Spectral features indicated high-velocity gas motions near galactic centers. Infrared luminosity patterns were consistent with accretion-driven heating. In some cases, emission line ratios pointed to active nuclei rather than stellar processes. Together, these signals converged on the presence of massive compact objects. Importantly, JWST data allowed separation between stellar and non-stellar contributions more effectively than before. Earlier observations often blurred star formation and accretion signatures. JWST's resolution and wavelength coverage reduced that ambiguity. This strengthened confidence that the observed energy output was genuinely associated with black hole activity. The host galaxies themselves added to the puzzle. Many appeared small and chemically primitive. Their stellar masses were modest. Their heavy element content was low. Under conventional sequencing, such galaxies should not yet host black holes of substantial mass. The mismatch between host maturity and black hole mass was pronounced. This mismatch undermined incremental explanations. Increasing accretion efficiency alone could not resolve it, because efficient accretion requires sustained gas supply and gravitational stability. Early galaxies were thought to be turbulent and fragmented, conditions unfavorable for prolonged central feeding. The statistical nature of the findings mattered as much as individual objects. JWST revealed that early massive black holes were not confined to rare environments. They appeared across a range of early galactic contexts. This reduced the plausibility of explanations relying on highly specific initial conditions. The implication was structural rather than numerical. If massive black holes were already present at these epochs, then their formation likely preceded or accompanied the earliest stages of galaxy assembly. This inverted the traditional order in which galaxies formed first and black holes followed. Such an inversion carries wide consequences. Black holes influence their surroundings through radiation and outflows. If present early, they could shape star formation and gas dynamics from the outset. Galaxy evolution models built without this influence would require revision. The discovery also affected interpretations of reionization. Early energetic sources contribute to ionizing radiation in the young universe. Massive black holes appearing early could alter timelines for when and how the intergalactic medium became ionized. Critically, these conclusions did not rest on a single detection or interpretation. Multiple independent surveys using JWST data converged on similar results. Different analysis methods yielded consistent mass and redshift estimates. The pattern was robust. What made this discovery unsettling was not that it contradicted theory outright, but that it exceeded the flexibility of existing adjustments. Parameter tuning could not easily reconcile the data without invoking fundamentally different initial conditions or formation pathways. The presence of massive black holes so early suggested that the universe was capable of producing dense structures more efficiently than assumed. Whether through direct collapse, primordial origins, or other mechanisms, the standard picture was incomplete. JWST did not resolve how these black holes formed. It established that they existed early and in significant numbers. That alone was sufficient to shift the problem from speculation to necessity. Any viable cosmological model must now account for these objects explicitly. The focus therefore moved from growth rates to origins. Understanding when massive black holes appear is one question. Understanding how they appear becomes unavoidable once their early presence is confirmed. This realization marked a turning point. Black hole formation was no longer a secondary detail appended to galaxy evolution. It became a central constraint shaping how the earliest cosmic structures must be understood. This shift also changed how uncertainty was treated within the field. Earlier models could tolerate rare anomalies because observational coverage was limited and incomplete. With JWST, the absence of an explanation became more visible than uncertainty itself. Researchers could no longer attribute discrepancies to selection effects or measurement error alone. The early universe now appeared structured, populated, and dynamically active in ways that exceeded conservative expectations. That realization did not invalidate decades of work, but it narrowed acceptable explanations. These observations forced theoretical revisions to move from optional refinements toward mandatory foundations. Why accretion alone cannot explain early supermassive black holes. Accretion has long been treated as the primary mechanism by which black holes grow. Matter drawn into a black hole releases energy as it heats and compresses, producing radiation that can be observed across vast distances. This process is well understood and has been studied in detail in nearby systems. Under normal conditions, accretion provides a predictable relationship between mass growth and energy output. That predictability is precisely what creates the problem in the early universe. Accretion is not unlimited. As in falling material radiates energy, that radiation exerts outward pressure. When the outward force balances gravity, further infall is suppressed. This balance defines a maximum steady growth rate that cannot be exceeded without destabilizing the flow. This limit, often treated as a fundamental constraint, implies exponential growth on a fixed timescale. A black hole can increase its mass by a certain factor over a given period, but it cannot accelerate arbitrarily. Even under ideal conditions, sustained growth from a small seed to a billion solar mass object requires hundreds of millions of years. The early universe does not provide that much time. JWST observations place massive black holes at epochs when the universe was only a few 100 million years old. In some cases, the available time is barely sufficient for even a single order of magnitude increase under maximal growth assumptions. One response has been to propose brief episodes of supercritical accretion. In these scenarios, black holes temporarily exceed standard limits due to changes in disk geometry or radiation trapping. While such behavior is theoretically possible, it introduces new constraints. Supercritical phases must be frequent, sustained, and coordinated across many systems to explain the observed population. This coordination is difficult to justify. Supercritical accretion requires specific conditions involving gas density, angular momentum transport, and radiative inefficiency. These conditions are unlikely to arise simultaneously and repeatedly across a wide range of early galaxies. Yet JWST data suggest early massive black holes were not rare exceptions. Gas availability presents another obstacle. Accretion depends on continuous gas supply delivered to the central region. Early galaxies were small and dynamically unstable. Their gas was subject to turbulence, fragmentation, and feedback from early star formation. Maintaining a steady inflow toward a central black hole under these conditions is problematic. Even if gas reaches the central region, it must lose angular momentum efficiently. Angular momentum acts as a barrier, preventing direct infall. In mature galaxies, bars and spiral structures help redistribute angular momentum. Early galaxies lack these organized features. Their chaotic structure inhibits sustained central feeding. Radiative feedback further complicates growth. As black holes accrete, they emit radiation and drive outflows. These processes heat and expel surrounding gas, reducing the available fuel. In small galaxies, this feedback is especially effective, as the gravitational potential is shallow. Rather than feeding growth, accretion can self-limit it. Chemical evidence adds to the difficulty. Many early galaxies hosting massive black holes show low metallicity. Heavy elements enhance cooling, allowing gas to collapse more efficiently. Primitive gas cools less effectively, making dense accretion flows harder to sustain. This works against rapid black hole growth, not in favor of it. Merger-driven growth also faces limitations. Black holes can gain mass by merging with others, but this requires prior formation of multiple seeds and sufficiently frequent galaxy mergers. Early merger rates are uncertain, but available evidence does not support merger-driven growth at the required scale and speed. Taken together, these factors constrain accretion-based explanations. Each proposed enhancement addresses one limitation while exacerbating another. Increasing accretion rates intensifies feedback. Increasing gas supply requires structures that early galaxies lacked. Increasing merger frequency requires prior black hole populations that themselves need explanation. The issue is not that accretion plays no role. It clearly does. The problem is that accretion alone cannot plausibly account for both the masses and the timing implied by JWST observations without invoking conditions that are extreme, finely tuned, and universally present. This realization shifts attention away from growth and toward initial conditions. If black holes began their evolution significantly more massive than stellar remnants, the growth problem becomes less severe. The required accretion time shortens, and the need for sustained supercritical phases diminishes. Accretion-based models implicitly assume small beginnings. JWST data challenge that assumption. They suggest that some black holes may have started large, bypassing the slow early stages entirely. In that context, accretion becomes a secondary process rather than the primary origin. This does not imply a single alternative mechanism. It implies that the standard growth narrative is incomplete. Accretion explains how black holes evolve once formed. It does not necessarily explain how the earliest massive ones came into existence. The significance of this limitation lies in its generality. It does not depend on one dataset or one interpretation. It follows from basic physics applied consistently across many observations. As more early black holes are detected, the burden on accretion-only explanations increases rather than diminishes. The failure of accretion to fully explain early supermassive black holes does not invalidate established theory. It highlights its boundaries. Understanding what lies beyond those boundaries requires examining formation pathways that operate before conventional growth begins. Direct collapse as an alternative formation path. Direct collapse refers to a pathway in which a black hole forms without passing through the conventional stellar life cycle. Instead of emerging from a supernova remnant, the black hole forms when a massive gas cloud collapses under its own gravity before fragmenting into stars. This idea was proposed to address situations where time and environmental conditions make stellar seed formation inefficient. In such cases, gravity overwhelms pressure and angular momentum barriers simultaneously. producing a compact object orders of magnitude more massive than any stellar black hole. Direct collapse does not require exotic physics, but it does require specific cosmic conditions. The conditions required for direct collapse are rare, but theoretically plausible in the early universe. The gas cloud must be extremely massive, typically exceeding 100,000 solar masses, and it must remain hot enough to avoid breaking apart. Cooling processes normally cause gas to fragment into stars, but if molecular hydrogen formation is suppressed, fragmentation can be delayed. This suppression can occur in regions exposed to intense ultraviolet radiation from nearby star-forming systems. Under these circumstances, the cloud collapses nearly monolithically, concentrating mass rapidly toward its center. Such environments were more common before galaxies developed stable internal structure globally. Direct collapse models also require low angular momentum within the collapsing gas. Rotation resists collapse by spreading material into disks rather than allowing it to fall inward. For direct collapse to proceed, mechanisms must efficiently redistribute or shed angular momentum. Turbulence, gravitational torques, and dynamical interactions within the gas cloud can contribute to this process. Simulations show that under the right conditions, angular momentum transport can occur rapidly enough to permit collapse. These requirements restrict where direct collapse can happen, but they do not make it impossible. Early cosmological environments provided temporary windows where these constraints aligned naturally across regions. If direct collapse occurs, the resulting object is not initially a conventional black hole. It forms as a massive, unstable structure supported briefly by radiation pressure. This phase is often described as a supermassive star or quasi-star. Its mass can exceed that of any normal star by several orders of magnitude. Such an object is short-lived. As internal support fails, it collapses rapidly, forming a black hole with a mass far larger than stellar remnants. This process effectively bypasses the slow early growth stage entirely. Accretion becomes secondary, shaping evolution rather than enabling initial existence itself under these circumstances broadly. Direct collapse offers an immediate solution to the timing problem posed by JWST observations. Starting from a massive seed reduces the required growth time dramatically. A black hole formed with a mass of 100,000 solar masses can reach supermassive scales with moderate accretion. The need for sustained supercritical growth phases is reduced or eliminated. This aligns more naturally with the turbulent, feedback-rich environments expected in early galaxies. As a result, direct collapse has gained renewed attention as a viable pathway within contemporary theoretical research, particularly when confronting early observational constraints that resist simpler explanations today across cosmology broadly. Despite its appeal, direct collapse is not a universal explanation. The required conditions are restrictive, and simulations indicate that only a fraction of early environments would permit it. This raises questions about abundance. JWST observations suggest that early massive black holes were not extremely rare. Reconciling this with a mechanism that operates only under specific circumstances remains challenging. Some models propose that direct collapse occurred preferentially in dense regions destined to become massive galaxies. Others suggest multiple formation channels operating in parallel during the universe's earliest structure-forming epochs, before feedback processes became dominant influences everywhere, uniformly across space and time. Another limitation involves observational confirmation. Direct collapse leaves few unambiguous signatures once the black hole has formed. The transient supermassive star phase is brief and difficult to detect. By the time a black hole becomes observable, its origin may be obscured by subsequent accretion and feedback. This makes direct collapse hard to verify directly. Evidence remains circumstantial, inferred from masses, metallicities, and timing, rather than direct observation of formation events. Consequently, acceptance depends on consistency with broader cosmological constraints, rather than isolated detection claims within limited datasets alone, requiring careful statistical interpretation across surveys and simulations alike, today globally considered. JWST contributes indirectly by narrowing plausible alternatives. As accretion-only models struggle and stellar seed pathways fail timing tests, mechanisms like direct collapse gain relative credibility. JWST's ability to characterize host galaxies strengthens these constraints. Low metallicity, compact structure, and early appearance collectively favor formation pathways that bypass extended stellar processing. While JWST cannot confirm direct collapse directly, it makes competing explanations increasingly difficult to sustain without invoking extreme assumptions about growth efficiency, environmental stability, or finely tuned initial conditions across large populations of early systems simultaneously, which weakens their explanatory power significantly within modern cosmological modeling frameworks today, overall globally accepted. Direct collapse, therefore, occupies an intermediate position. It is neither speculative invention nor established fact. It is a theoretically grounded response to specific empirical tensions. Its plausibility rises as observational constraints tighten, even as uncertainties remain. Importantly, direct collapse does not exclude other pathways. It may operate alongside stellar collapse and mergers, contributing a subset of black hole seeds. Understanding its role requires integrating simulation, observation, and theory across multiple scales spanning early universe physics, galactic dynamics, and long-term evolutionary outcomes that shape observable populations over cosmic time, rather than single mechanisms acting alone in isolation anywhere universally across models. The relevance of direct collapse extends beyond black hole formation. It implies that the early universe could produce extreme density contrasts rapidly, without prolonged hierarchical buildup. This challenges assumptions about smooth structure growth following inflation. If direct collapse occurred frequently, it suggests that initial fluctuations were capable of nonlinear collapse sooner than expected. That possibility connects black hole origins to fundamental cosmological conditions, linking small-scale physics to large-scale structure in a way that current models only partially capture, and therefore motivates further observational scrutiny using future surveys, simulations, and theoretical refinements aimed at reconciling early complexity with cosmic evolution consistently. JWST observations of metal-poor early galaxies. One of the most consequential findings enabled by the James Webb Space Telescope is the detailed measurement of chemical composition in very early galaxies. Chemical composition, often described through metallicity, serves as a record of prior stellar activity. Elements heavier than hydrogen and helium are produced almost entirely through nuclear processes inside stars. Their presence signals repeated cycles of star formation, stellar death, and enrichment of surrounding gas. Before JWST, metallicity estimates at high redshift were crude and indirect. Observations relied on limited spectral lines, often blended or obscured by distance and dust. As a result, early galaxies were frequently assumed to be chemically immature, but the degree of immaturity remained uncertain. JWST's infrared spectroscopy changed this by resolving diagnostic emission lines with enough clarity to quantify elemental abundances directly. What emerged from these observations was a population of galaxies with extremely low heavy element content. In several cases, oxygen, carbon, and nitrogen abundances were measured at levels far below those seen in later galaxies. Some systems contained less than 1% of the heavy element concentration typical of the Milky Way. This places them among the most chemically primitive galaxies ever observed. These measurements carry specific implications. Even a single generation of massive stars enriches surrounding gas relatively quickly. Supernova explosions disperse heavy elements efficiently, raising metallicity on timescales of tens of millions of years. Galaxies with sustained star formation therefore show measurable chemical evolution early. The absence of such enrichment suggests either very recent star formation or minimal stellar processing overall. JWST observations complicate this interpretation by revealing structural maturity alongside chemical simplicity. Some metal-poor galaxies appear compact, centrally concentrated, and dynamically organized. Their light profiles resemble systems that, under conventional models, should have experienced multiple stellar generations. The coexistence of order and chemical youth challenges standard evolutionary sequencing. This contradiction matters because metallicity directly affects gas behavior. Heavy elements enhance cooling by providing additional radiative pathways. Low metallicity gas cools less efficiently, resisting fragmentation and slowing star formation. Yet JWST observes active systems operating under these chemically primitive conditions. This suggests that early star formation proceeded differently than later analogues. The presence of massive black holes within some of these metal-poor galaxies intensifies the tension. Black hole growth through stellar remnants implies prior star formation sufficient to produce massive progenitors. That process should leave chemical signatures. Their absence indicates that black holes may have formed independently of extensive stellar activity. This inference does not rely on a single object. JWST surveys have identified multiple chemically unevolved galaxies, hosting energetic central sources. The pattern suggests a broader population rather than isolated anomalies. Statistical significance strengthens the case that early black hole formation may not require enriched environments. Metallicity also constrains timelines. Chemical youth implies limited elapsed time since the onset of star formation. When such galaxies host massive black holes, the available window for conventional growth shrinks further. This exacerbates the timing problem already posed by early black hole detections. Alternative explanations have been considered. One possibility is that heavy elements are present but obscured. JWST's wavelength coverage reduces this likelihood. Infrared diagnostics are less sensitive to dust extinction, and line ratios support genuinely low abundances. Another possibility is that metals have been expelled by feedback. While outflows occur, removing nearly all enrichment without disrupting structure is difficult. The simplest interpretation is that some early galaxies formed massive central objects before undergoing extensive chemical evolution. This reverses the traditional order in which stars enrich gas first, enabling later black hole growth. Instead, black holes may have influenced their host galaxies from the outset. This scenario aligns with models where black holes form from large gas collapses rather than stellar remnants. Such collapses can occur in chemically pristine environments. JWST's metallicity measurements provide circumstantial support for this pathway by showing that enrichment is not always a prerequisite for black hole presence. These findings also affect interpretations of early galaxy populations more broadly. Metallicity distributions influence estimates of star formation efficiency, feedback strength, and ionizing photon production. Revising chemical timelines alters models of reionization and early cosmic heating. JWST does not prove a single formation mechanism. It establishes constraints that any viable explanation must satisfy. Low metallicity combined with structural maturity and energetic central activity narrows the range of acceptable models significantly. The importance of these observations lies in their consistency. Across independent studies, chemically primitive galaxies appear more common and more complex than anticipated. This consistency shifts chemical simplicity from an assumption to an observed property with explanatory power. By revealing that some early galaxies remained chemically unevolved while hosting massive compact objects, JWST forces a reconsideration of how quickly structure and complexity emerged. The early universe appears capable of producing organized systems before completing the chemical processes once thought necessary. These results do not resolve the black hole origin problem, they deepen it. By removing chemical enrichment as a prerequisite, they open formation pathways previously considered marginal. In doing so, they push cosmology toward models where early structure formation was faster, denser, and less dependent on stellar recycling than long assumed. Black holes without mature stellar populations. One of the most challenging implications of James Webb Space Telescope observations is the growing number of systems in which black hole activity appears without evidence of a mature stellar population. In standard cosmological models, stars are treated as the primary drivers of structure. They form first, generate heavy elements, and create the physical conditions under which black holes are expected to emerge and grow. When black holes are observed in environments lacking these prerequisites, the assumed developmental sequence no longer holds. Mature stellar populations leave multiple independent signatures. They contribute to chemical enrichment, increase total stellar mass, and produce recognizable spectral features. Even short-lived generations of massive stars enrich their surroundings efficiently. Supernova explosions disperse heavy elements on short timescales, and stellar radiation reshapes the interstellar medium through heating and ionization. A galaxy that has hosted substantial star formation should therefore display measurable metallicity, structured stellar light, and feedback-driven gas dynamics. JWST has identified several early systems where these indicators are weak or nearly absent, yet central energy output suggests the presence of massive black holes. These galaxies appear compact and faint in stellar emission, while their infrared spectra point toward non-stellar heating mechanisms. The mismatch between minimal stellar maturity and apparent black hole activity is not subtle. It recurs across multiple observations and redshift ranges. This pattern undermines the assumption that black holes must be downstream products of stellar evolution. If black holes formed exclusively from massive stars, then galaxies hosting them should preserve evidence of those progenitors. The absence of such evidence suggests either that stellar populations were somehow removed after formation, or that black holes formed through alternative pathways that do not require prior stellar buildup. Removal scenarios face significant challenges. Tidal stripping strong enough to eliminate stellar populations typically leaves clear dynamical disturbances, including asymmetries, tidal tails, or disrupted morphologies. Many of the observed systems show no such features. Feedback-driven evacuation presents similar difficulties. While energetic outflows can expel gas and suppress future star formation, they do not erase stellar mass that has already formed. Explaining near-total absence of stellar maturity through removal alone therefore requires finely tuned conditions that are not supported by current observations. Observational bias is another possibility. Early stellar populations may exist, but remain faint or diffuse. JWST's sensitivity substantially reduces this concern. Its ability to detect low-mass stars and weak stellar continua at high redshift exceeds that of previous observatories. While it is possible that some stellar components remain below detection thresholds, the combined absence of stellar mass, metallicity, and feedback signatures is difficult to attribute solely to observational limits. These constraints shift attention toward formation order. If black holes formed before extensive star formation, then weak stellar signatures would be expected rather than anomalous. In this scenario, black holes are not products of galactic maturity, but contributors to it. Their gravitational and radiative influence shapes gas dynamics before stars dominate the energy budget. This inversion has theoretical grounding. Under certain early universe conditions, large gas clouds can collapse directly into dense central objects without fragmenting into stars, particularly if cooling is delayed or angular momentum is efficiently redistributed. In such cases, a massive compact object forms first, with star formation occurring later within a gravitational potential already dominated by the central mass. JWST's observations are consistent with this sequence. Systems exhibiting active nuclei alongside minimal stellar development suggest that black holes may act as early organizers of structure. Rather than emerging from galaxies, they may help define them. Gas inflow, heating, and ionization would proceed differently in the presence of an early compact mass, altering subsequent star formation patterns. This interpretation changes how early galaxies are classified. objects previously described as primitive or underdeveloped may instead represent alternative evolutionary branches. Their apparent simplicity does not indicate uniform immaturity. It reflects divergence in formation pathways rather than failure to progress. The absence of mature stellar populations also affects feedback assumptions. In standard models, stars regulate black hole growth through supernova-driven turbulence and gas depletion. When stars are scarce, this regulatory mechanism weakens. Black holes accrete under different constraints, potentially altering early growth behavior. This does not imply unlimited growth, as gas supply, angular momentum, and radiation pressure still impose limits, but it does change the relative balance between stellar and black hole feedback. Infrared emission further complicates interpretation. In several of these systems, infrared excess initially attributed to star formation becomes difficult to justify once stellar indicators are examined closely. Dust heating without corresponding stellar mass suggests alternative energy sources. Accreting compact objects can produce thermal signatures that resemble stellar activity without requiring large stellar populations. This complicates star formation rate estimates at high redshift and reinforces the need for careful separation of stellar and non-stellar contributions. Chemical evidence strengthens the case. Even brief episodes of massive star formation rapidly enrich surrounding gas. The persistence of extremely low metallicity alongside evidence of central energy release implies that such episodes were either absent or highly limited. This constrains how quickly stars could have formed relative to black hole activity, and supports the idea that black holes preceded widespread stellar enrichment in these systems. Structural consequences follow from this ordering. A black hole forming prior to significant stellar buildup alters the gravitational potential early. Gas settling, fragmentation, and cooling proceed under different conditions than in star-first scenarios. Stars forming later would therefore emerge within environments shaped by an existing compact mass, potentially producing stellar distributions unlike those seen in galaxies where stars formed first. These systems also challenge common metrics of galaxy evolution. Stellar mass is often used as a proxy for evolutionary stage. Black holes without accompanying stellar mass disrupt this assumption. A galaxy's apparent youth may conceal complex internal dynamics driven by non-stellar components that dominate early energetics. JWST's contribution lies in revealing these mismatches directly. By resolving both stellar and non-stellar components within the same systems, it allows comparison rather than inference. The resulting picture is not one of rare anomalies, but of recurring configurations that demand explanation. Importantly, these observations do not eliminate stellar-based black hole formation. They indicate coexistence of pathways. Some black holes likely formed from stars, others from direct gas collapse, and some through hybrid processes. The early universe appears to have supported multiple routes simultaneously. Recognizing this diversity is essential. Treating black hole formation as a single process phenomenon obscures the complexity revealed by observation. JWST data suggest that early cosmic environments were capable of producing compact, massive objects under a wider range of conditions than previously assumed. Black holes without mature stellar populations therefore represent more than an observational curiosity. They challenge how causality is assigned in galaxy formation. Stars no longer appear as universal prerequisites. In some cases, they may be secondary outcomes. This realization forces theoretical models to accommodate sequences in which gravity organizes matter before stars dominate energetics. Such models remain under development, but their relevance is increasingly difficult to ignore. The significance of these systems is not that they overturn all prior understanding, but that they expose its limits. They demonstrate that the early universe was not bound to a single developmental order. Instead, it was capable of assembling massive structures through multiple channels, some of which leave minimal stellar footprints. Understanding these channels is central to interpreting JWST's broader implications. If black holes can arise independently of mature stellar populations, then assumptions about timing, feedback, and chemical evolution must be revised accordingly. Theoretical foundations of primordial black holes. Primordial black holes differ fundamentally from black holes formed through stellar or galactic processes. Their defining characteristic is timing. Rather than emerging billions of years after the Big Bang, through stellar collapse or gas accretion, primordial black holes are theorized to have formed directly from density fluctuations in the early universe itself. Their existence depends not on astrophysical evolution, but on conditions present during the universe's earliest moments. The theoretical basis for primordial black holes arises from standard cosmology rather than speculative physics. In the first fractions of a second after the Big Bang, the universe was extremely hot, dense, and rapidly expanding. Matter and radiation existed in a tightly coupled state, and small variations in density were imprinted across space. These fluctuations are well established. They are observed indirectly today through temperature variations in the cosmic microwave background. Under normal circumstances, density fluctuations evolve gradually. Regions slightly denser than average attract more matter, eventually forming stars and galaxies over hundreds of millions of years. However, if a fluctuation exceeds a critical threshold, gravitational collapse can occur almost immediately. In the early universe, where pressure and density were extreme, such collapse could produce black holes directly, without passing through intermediate structures. This mechanism was first formalized in the 1960s, when researchers explored the consequences of early universe density inhomogeneities. They found that sufficiently overdense regions could collapse into black holes if their size fell within the cosmic horizon and their density contrast exceeded a specific limit. The physics involved is classical general relativity applied under early universe conditions, not an extension beyond established theory. Primordial black hole formation does not require stars, heavy elements, or galaxies. It relies solely on gravity acting on matter when the universe was young enough for extreme densities to exist naturally. This makes primordial black holes fundamentally different from all later formed compact objects. One consequence of this formation pathway is a wide possible mass range. The mass of a primordial black hole is tied to the horizon mass at the time of collapse. Black holes forming earlier would be smaller, those forming later would be larger. As a result, primordial black holes could theoretically span masses from microscopic scales to thousands or even millions of solar masses. This flexibility is both an advantage and a complication. It allows primordial black holes to serve as potential seeds for later supermassive black holes. At the same time, it requires constraints to prevent overproduction. Too many primordial black holes would disrupt nucleosynthesis, alter cosmic expansion, or conflict with observed radiation backgrounds. For decades, these constraints led many researchers to treat primordial black holes as mathematically possible but astrophysically irrelevant. Observational limits from gamma rays, gravitational lensing, and cosmic background radiation appeared to rule out most mass ranges. As a result, primordial black holes were often relegated to footnotes rather than central models. That position began to soften as new observational puzzles emerged. The discovery of massive black holes at early times strained stellar-based explanations. At the same time, dark matter remained undetected through particle searches. Primordial black holes offered a single framework capable of addressing both issues, at least in principle. Importantly, primordial black holes do not require new particles or forces. They arise naturally from gravitational physics under extreme conditions. Their plausibility depends on the amplitude and distribution of early density fluctuations, which are themselves tied to inflationary models. Inflation, the rapid expansion thought to have occurred shortly after the Big Bang, plays a central role. Small deviations in inflationary dynamics can amplify density fluctuations on specific scales. Certain inflation models predict enhanced fluctuations that could produce primordial black holes efficiently, without violating observational constraints. This connection links primordial black holes to fundamental cosmology. Their existence would encode information about inflation that cannot be accessed through other means. In this sense, they act as fossils of the universe's earliest physical processes. Despite this appeal, primordial black hole theory remains tightly constrained. Observations limit their abundance across most mass ranges. However, constraints are not absolute. They depend on assumptions about clustering, evaporation rates, and interactions. Revisions to any of these factors can reopen parameter space previously thought closed. One such revision concerns black hole evaporation. Hawking radiation predicts that small black holes should lose mass and eventually disappear. For decades, this was treated as definitive. However, recent theoretical work suggests that evaporation may slow dramatically at small scales, potentially leaving long-lived remnants. If correct, this alters survival expectations for low-mass primordial black holes. Primordial black holes also evade certain detection methods. Unlike stellar black holes, they may lack accretion disks or luminous environments. They interact primarily through gravity. This makes them difficult to observe directly, especially at small masses. Absence of evidence is therefore not evidence of absence. From a theoretical standpoint, primordial black holes occupy a unique category. They are neither astrophysical byproducts nor exotic objects requiring new physics. They are consequences of known physics applied to early universe conditions that remain imperfectly constrained. JWST's relevance lies in context rather than direct detection. By revealing early massive black holes and chemically primitive systems, it strengthens the motivation to revisit formation pathways that operate before stars and galaxies. Primordial black holes offer one such pathway. The significance of primordial black holes is not that they are confirmed, but that they remain viable under conditions where other explanations struggle. Their theoretical foundations are well established, their parameter space is constrained but not eliminated, and their implications intersect multiple unresolved problems. Understanding whether primordial black holes exist requires integrating cosmology, particle physics, and astrophysical observation. JWST contributes by sharpening the questions rather than providing definitive answers. It pushes black hole origins back toward the earliest moments of the universe, where primordial processes become relevant. In this way, primordial black holes shift from speculative concept to necessary consideration. They represent a class of solutions grounded in established physics, capable of addressing observations that resist simpler explanations. Whether they are real remains uncertain, but the theoretical foundation supporting them is no longer peripheral. Mass ranges of hypothetical primordial black holes. One of the most distinctive features of primordial black holes is the breadth of masses they could theoretically possess. Unlike stellar black holes, whose masses are constrained by the physics of stellar evolution, primordial black holes derive their mass from cosmological conditions at the moment of formation. This makes their possible mass range far wider than that of any other black hole population. The determining factor is the horizon mass of the universe. At the time a primordial black hole forms, the horizon defines the maximum region over which causal processes can operate. Any overdensity collapsing into a black hole cannot exceed the mass contained within that horizon. As the universe expands, the horizon mass increases, meaning primordial black holes forming at later times would be more massive than those forming earlier. In the earliest moments after the Big Bang, the horizon mass was extremely small. Black holes forming during this phase could have masses comparable to mountains, asteroids, or even smaller scales. As time progressed, the horizon mass grew rapidly. Within fractions of a second, it became possible for black holes with stellar-scale masses to form. In later early universe epochs, masses exceeding those of typical stars also become theoretically accessible. This leads to a continuous spectrum rather than discrete categories. primordial black holes could, in principle, exist at nearly any mass scale, bounded only by formation timing and cosmological constraints. This stands in sharp contrast to stellar black holes, which cluster around a narrow mass range defined by nuclear fusion limits and supernova physics. Each mass range carries different observational consequences. Very low-mass primordial black holes would be extremely difficult to detect directly. They would emit negligible radiation, interact weakly with surrounding matter, and reveal themselves only through subtle gravitational effects. Their existence would primarily influence cosmological measurements rather than individual astrophysical systems. Intermediate mass primordial black holes, ranging from asteroid mass to planetary mass, are of particular interest. These objects are massive enough to produce measurable gravitational effects, but small enough to evade many detection methods. They could pass through stellar systems with minimal disruption, leaving little trace unless precise monitoring is available. Higher mass primordial black holes overlap with ranges traditionally associated with stellar remnants. In this regime, distinguishing primordial from stellar origin black holes becomes challenging. Mass alone is insufficient. Context, environment, and formation history must be considered. A black hole of several solar masses could plausibly arise from either pathway, complicating classification. At the upper end of the spectrum, primordial black holes with masses tens of thousands or even millions of solar masses have been proposed. These objects are particularly relevant to discussions of early supermassive black hole formation. If such massive primordial seeds formed, they would drastically reduce the need for prolonged growth through accretion. However, large primordial black holes face stronger observational constraints. Objects of significant mass would distort spacetime enough to produce detectable gravitational lensing. They would also influence the dynamics of stars and gas in their vicinity. Surveys have placed limits on the abundance of such objects, ruling out scenarios where they dominate cosmic mass density. Despite these constraints, narrow mass windows remain open. Certain ranges are poorly constrained due to observational limitations or theoretical uncertainty. These windows are where primordial black holes remain viable, dark matter candidates, and plausible contributors to early black hole populations. Hawking radiation plays a central role in defining which mass ranges can persist today. According to theory, black holes emit radiation at a rate inversely proportional to their mass. Extremely small black holes should evaporate rapidly, disappearing entirely over cosmic time. Larger ones evaporate more slowly, surviving to the present day. The precise mass threshold for survival depends on evaporation dynamics. Classical estimates suggest that black holes below roughly asteroid mass would have evaporated by now. However, recent theoretical work questions whether evaporation proceeds uninterrupted to zero mass. If evaporation slows or halts at small scales, then remnants could persist across mass ranges previously considered excluded. This uncertainty reopens discussion about low-mass primordial black holes. Objects once dismissed as impossible survivors may instead exist as stable or long-lived remnants. Their mass would be small, but their gravitational influence would remain. This possibility complicates efforts to rule out primordial black holes purely through evaporation arguments. Mass distribution also affects clustering behavior. Primordial black holes may not be uniformly distributed. Early universe conditions could lead to clustering on certain scales, altering their collective gravitational impact. Clustering changes how observational constraints apply, as groups of small black holes can mimic the effects of fewer large ones. JWST does not directly measure primordial black hole masses, but its discoveries influence which mass ranges are most relevant. The presence of massive black holes early in cosmic history makes higher mass primordial seeds more attractive. At the same time, unresolved dark matter remains consistent with lower mass populations. The challenge is that no single mass range solves all problems simultaneously. Large primordial black holes help explain early supermassive objects, but face observational limits. Small ones evade detection, but struggle to account for all dark matter. Intermediate masses occupy uncertain territory, constrained but not eliminated. This complexity is not a weakness of the theory. It reflects the diversity of early universe conditions. Primordial black holes may not form with a single characteristic mass. Instead, they could populate a spectrum shaped by inflationary physics, density fluctuations, and cosmic expansion. Understanding which mass ranges are viable requires combining cosmological data, gravitational lensing surveys, background radiation measurements, and dynamical studies. Each method probes different scales and carries different assumptions. The resulting picture is fragmented but evolving. The importance of primordial black hole mass ranges lies in their explanatory reach. They connect early universe physics with present-day observations across multiple domains. As constraints tighten and models refine, some ranges will close while others remain open. JWST contributes by sharpening the need for early massive seeds. That pressure does not select a specific mass, but it narrows the conversation. Any viable formation model must now accommodate objects appearing early and growing quickly. Primordial black holes remain among the few candidates capable of spanning the required mass scales without violating known physics. Hawking radiation and the expected fate of small black holes. Hawking radiation occupies a central role in debates about the survival of small black holes because it defines whether such objects can persist across cosmic timescales or inevitably vanish. The concept describes a quantum mechanical process through which black holes lose mass. According to the theory, black holes are not perfectly black, but emit extremely small amounts of radiation due to quantum effects near the event horizon. This emission carries energy away from the black hole, causing it to lose mass and gradually shrink. Crucially, the rate of this mass loss increases as the black hole becomes smaller. For large black holes, this effect is effectively irrelevant. Supermassive and stellar mass black holes lose energy through Hawking radiation at rates so low that evaporation timescales exceed the current age of the universe by many orders of magnitude. Their evolution is dominated by accretion and mergers rather than quantum emission. For sufficiently small black holes, however, the situation changes fundamentally. As mass decreases, Hawking radiation intensifies, leading to faster mass loss. This creates a feedback process in which shrinking accelerates evaporation. This prediction led to a widely accepted conclusion: primordial black holes below a certain mass threshold should not survive to the present day. According to standard calculations, any black hole formed with a mass below roughly that of a large asteroid would have evaporated completely within the age of the universe. This conclusion shaped cosmological thinking for decades. If Hawking radiation proceeds uninterrupted and behaves exactly as predicted across all mass scales, then only relatively massive primordial black holes could remain today. As a result, tiny primordial black holes were long treated as cosmologically irrelevant. They were assumed to be short-lived features of the early universe, disappearing long before galaxies, stars, or complex structure formed. Under this framework, discussions of primordial black holes focused almost exclusively on higher mass ranges, while low-mass populations were excluded on theoretical grounds rather than observational ones. These expectations impose strong constraints on allowed primordial black hole mass distributions. Certain mass ranges would have produced observable radiation backgrounds during evaporation, particularly in gamma rays. The absence of such backgrounds was used to exclude those scenarios. Hawking radiation thus became one of the most powerful tools for ruling out large classes of primordial black hole models. Over time, the theoretical parameter space narrowed substantially. However, the foundation of Hawking radiation itself remains incomplete. The theory emerges from combining quantum field theory with curved spacetime, but without a complete theory of quantum gravity. It relies on semi-classical approximations that treat space-time as smooth while allowing quantum effects in fields near the event horizon. This approach is mathematically consistent within certain limits, but it has never been tested experimentally in the regime where evaporation becomes dominant. Direct detection of Hawking radiation is beyond current technological capability. Even for stellar mass black holes, the predicted radiation is far weaker than cosmic background noise. As a result, Hawking radiation remains a theoretical construct rather than an empirically verified phenomenon. This gap between theory and observation introduces uncertainty, particularly when extrapolating evaporation behavior down to extremely small mass scales. In recent years, this uncertainty has received increased attention. Several theoretical studies have revisited the assumption that evaporation proceeds smoothly and inevitably to zero mass. Some models suggest that as a black hole approaches minimal mass, quantum gravitational effects could alter the evaporation process. Instead of accelerating indefinitely, mass loss may slow dramatically or even cease altogether. In these scenarios, black holes would not disappear but would stabilize as long-lived or permanent remnants. Such remnants would retain mass and gravitational influence while emitting little or no radiation. From an observational perspective, they would be extremely difficult to detect, yet their existence would fundamentally change the survival prospects of small primordial black holes. Mass ranges previously excluded on evaporation grounds would become viable again, provided remnants form. This possibility does not require radical departures from known physics. It arises from acknowledging uncertainty where theoretical control is weakest. Near the Planck scale, where black holes would become extremely small, current theories lack predictive certainty. Different approaches to quantum gravity yield different outcomes, and none have been experimentally validated. As a result, evaporation behavior near minimal mass remains an open question rather than a settled conclusion. Because of this, constraints on primordial black hole populations depend sensitively on assumptions about evaporation. If evaporation proceeds uninterrupted, small black holes vanish. If remnants form, they persist. This sensitivity complicates efforts to definitively exclude primordial black holes from cosmological relevance. It also demonstrates how theoretical uncertainty can preserve otherwise excluded scenarios. The difficulty is compounded by the observational subtlety of small black holes. Even if remnants exist, they would interact primarily through gravity. Individually, their gravitational influence would be negligible. They would emit no light, produce no strong accretion signatures, and generate no distinctive electromagnetic signals. As a result, absence of detection cannot be equated with absence of existence. This places Hawking radiation in a pivotal position. It governs whether small primordial black holes are transient or persistent, whether they vanish early or remain today as dark components. The uncertainty surrounding evaporation reflects deeper, unresolved questions in fundamental physics. Until quantum gravity is experimentally constrained, the fate of small black holes remains provisional rather than definitive. James Webb Space Telescope observations do not directly address Hawking radiation. JWST operates in infrared wavelengths and cannot observe quantum evaporation processes. However, JWST alters the broader context in which evaporation arguments are evaluated. By revealing black holes and compact structures at earlier times than expected, it increases the relevance of primordial survival questions. If black holes appear early, then understanding which ones endure becomes essential. Previously, evaporation arguments were often used as closing statements. Small primordial black holes were dismissed, allowing focus to shift elsewhere. That rhetorical role has changed. Hawking radiation now functions as a conditional boundary rather than a final verdict. It defines what can be excluded under specific assumptions while leaving open alternative outcomes under others. This shift reflects a broader change in cosmology. Increasingly, theories are evaluated not as absolute truths, but as frameworks with domains of validity. Hawking radiation exemplifies this approach. Its predictions are robust in some regimes and uncertain in others. Recognizing this distinction prevents overextension of conclusions beyond their theoretical support. The survival of small primordial black holes therefore remains unresolved. This unresolved status sustains their relevance in discussions of dark matter, early structure formation, and gravitational phenomenology. Hawking radiation acts simultaneously as a constraint and a source of uncertainty. It limits some possibilities while preserving others. This dual role ensures that evaporation physics remains central rather than peripheral. As long as evaporation behavior at the smallest scales is not experimentally verified, primordial black holes cannot be conclusively excluded. Their relevance depends not on direct detection, but on the boundaries of theoretical confidence. Hawking radiation thus sits at the intersection of black hole physics, quantum theory, and cosmology. Questions about the smallest scales influence interpretations of the largest structures. JWST's discoveries make this intersection more consequential by pushing black hole formation closer to the beginning of cosmic history. The question is no longer simply whether Hawking radiation exists, but how it behaves under extreme conditions where theory is incomplete. That distinction matters. If evaporation halts or slows, the cosmological role of primordial black holes changes dramatically. If it does not, their influence fades. At present, neither outcome can be ruled out with certainty. Until experimental or observational advances constrain quantum gravity, Hawking radiation will continue to define an open boundary. It frames what can be ruled out and what remains possible. In the context of early universe discoveries, that boundary has gained renewed importance. The fate of small primordial black holes therefore remains an unresolved consequence of deeper theoretical uncertainty. Resolving it will likely require advances in fundamental physics rather than astronomy alone. Until then, Hawking radiation remains a governing assumption rather than a settled fact, and primordial black holes remain conditionally viable components of cosmic history. Recent revisions to Hawking evaporation models. Hawking radiation has long been treated as a definitive process governing the ultimate fate of small black holes. In its original formulation, black holes radiate energy thermally due to quantum effects near the event horizon, causing them to lose mass over time. As mass decreases, temperature increases, accelerating evaporation until the black hole vanishes entirely. This framework implies a clear outcome. Sufficiently small black holes cannot survive for the age of the universe. For decades, this conclusion shaped cosmological thinking. Any primordial black hole below a certain mass threshold was assumed to have evaporated completely. This assumption allowed researchers to exclude entire classes of primordial black holes from consideration. It became embedded in constraint calculations, population models, and dark matter analyses. However, this conclusion depends on extending semi-classical physics into regimes where it may no longer apply reliably. Hawking radiation is derived by combining quantum field theory with classical general relativity. While this approach works well at large scales, it becomes uncertain as black holes shrink. Near the end of evaporation, space-time curvature becomes extreme, and quantum gravity effects are expected to dominate. Because no complete theory of quantum gravity exists, predictions about the final stages of evaporation remain speculative. In recent years, several theoretical studies have revisited these assumptions. Instead of treating evaporation as a smooth and inevitable process down to zero mass, newer models explore how quantum effects might alter or interrupt evaporation at small scales. These revisions do not reject Hawking radiation outright. Rather, they question whether its simplest extrapolation remains valid under all conditions. One class of models suggests that evaporation may slow dramatically as a black hole approaches a minimal mass. In these scenarios, back-reaction effects become significant. The emitted radiation alters the space-time structure near the horizon in ways that suppress further emission. As a result, mass loss becomes increasingly inefficient, extending the black hole's lifetime far beyond classical estimates. Another possibility involves the formation of stable remnants. In these models, evaporation halts at a finite mass due to quantum gravitational effects. The black hole transitions into a compact object that no longer radiates appreciably. Such remnants would be extremely small, cold, and difficult to detect, but they would retain gravitational mass. This outcome preserves conservation laws while avoiding complete disappearance. These ideas are not purely speculative. They arise naturally in several approaches to quantum gravity, including loop gravity-inspired models and string-theoretic considerations. While none of these frameworks is experimentally confirmed, they demonstrate that complete evaporation is not the only consistent outcome within theoretical physics. The implications for primordial black holes are substantial. If evaporation slows or stops, then low-mass primordial black holes could survive to the present day. Mass ranges previously ruled out become viable again. Constraints based on expected gamma-ray backgrounds weaken. Population limits must be recalculated under revised assumptions. Importantly, these revisions do not require fine-tuning. They emerge from acknowledging that semi-classical approximations break down near Planck scale regimes. Since no observations currently probe these scales directly, the correct behavior remains unknown. Theoretical uncertainty therefore translates into cosmological uncertainty. This has prompted a shift in how evaporation constraints are treated. Rather than absolute exclusions, they are increasingly presented as conditional. Results depend on assumptions about end-stage physics. Different evaporation models yield different survival thresholds and observational signatures. Some researchers have explored hybrid scenarios, where evaporation proceeds normally down to a certain mass, then transitions into a remnant phase. Others propose oscillatory behavior or intermittent emission. While details vary, the common theme is that the final outcome is not settled. These developments complicate the interpretation of null results. Failure to detect evaporation signatures no longer strongly disfavors primordial black holes. Instead, it may indicate that evaporation behaves differently than expected. Absence of radiation can reflect suppressed emission rather than absence of objects. JWST does not directly test evaporation physics. However, its discoveries increase the relevance of these revisions. If black holes appear very early, then primordial formation pathways gain importance. That, in turn, makes survival physics critical. Whether primordial black holes persist depends on evaporation behavior. Revised evaporation models also influence dark matter discussions. Small primordial black holes or remnants could contribute to unseen mass without violating observational bounds. This possibility remains constrained, but it cannot be dismissed outright. Evaporation uncertainty keeps this option open. The broader implication is methodological. Cosmology often relies on combining incomplete theories across scales. When foundational physics is uncertain, conclusions must be treated cautiously. Hawking radiation illustrates how theoretical confidence can outpace empirical verification. These revisions do not overturn established results. Large black holes still evaporate negligibly slowly. Stellar and supermassive black holes are unaffected. The uncertainty applies primarily to the smallest masses, precisely where primordial black holes are most relevant. As a result, the status of primordial black holes has shifted from excluded to conditional. Their existence depends on unresolved physics rather than observational contradiction. This shift changes how JWST findings are contextualized. Early massive black holes encourage broader consideration of primordial scenarios, including those involving small-scale physics. Future progress will require advances beyond astronomy. Laboratory analogues, quantum gravity theory, and perhaps gravitational wave signatures may eventually constrain evaporation behavior. Until then, revised models remain plausible alternatives. In the meantime, cosmological interpretations must accommodate uncertainty. Hawking radiation no longer provides a definitive cutoff. It defines a range of possibilities bounded by theory rather than observation. This uncertainty reinforces a central theme emerging from JWST discoveries. The early universe may not conform to simplified narratives built on later time physics. Processes operating near fundamental limits can produce outcomes that remain poorly constrained. Revising evaporation models reflects an evolving understanding of black holes as physical systems rather than idealized objects. As observations push closer to cosmic origins, theoretical assumptions face renewed scrutiny. Hawking radiation remains a cornerstone of black hole theory, but its final implications are not fully known. Recognizing that limitation preserves theoretical flexibility while avoiding premature exclusion of viable scenarios. In this context, primordial black holes persist as candidates shaped as much by uncertainty as by evidence. Revised evaporation models ensure that their possible survival remains a legitimate topic of scientific inquiry rather than a closed case. JWST. Evidence that challenges complete evaporation. The James Webb Space Telescope does not observe Hawking radiation, nor does it detect primordial black holes directly. Its relevance to evaporation theory lies elsewhere. By reshaping expectations about when and how black holes appear, JWST alters the assumptions under which evaporation arguments are applied. Observational context matters. When black holes are pushed closer to the beginning of cosmic history, questions about their survival can no longer be treated as abstract theoretical exercises. Complete evaporation models rely on two assumptions operating together. First, that small black holes form in limited numbers. Second, that they evaporate smoothly and fully over cosmic time. JWST observations place pressure on both assumptions, not by contradiction, but by changing the landscape in which they are evaluated. The first pressure point is abundance. JWST has shown that massive black holes existed early and in numbers that exceed prior expectations. This implies either highly efficient growth or a substantial population of early seeds. If early black hole formation was more common than assumed, then it becomes statistically plausible that a spectrum of black hole masses formed simultaneously, including small ones. Evaporation arguments become population-dependent rather than binary. The second pressure point is timing. JWST pushes black hole relevance closer to epochs where primordial processes dominate. When formation is shifted toward the first few 100 million years, survival over cosmic time becomes more sensitive to the details of evaporation physics. Small differences in early conditions can translate into large differences in present-day outcomes. JWST also reveals environments that lack strong electromagnetic signatures typically associated with black hole activity. Some early systems show gravitational influence without corresponding luminous output. While these observations are not interpreted as evidence of small black holes, they demonstrate that black holes can exist in states that are observationally quiet. This undermines assumptions that absence of radiation implies absence of compact objects. Evaporation constraints often depend on expected radiation backgrounds. Small black holes are predicted to emit high-energy radiation as they evaporate. Surveys have searched for these signatures and found none at the expected levels. However, if black holes spend much of their lifetime in low-emission states or transition into remnant phases, those constraints weaken. JWST reinforces the idea that observational silence does not equate to physical absence. Another factor concerns chemical environments. JWST has identified chemically primitive systems hosting massive black holes. These environments suggest that black hole formation and evolution can proceed without extensive interaction with enriched matter. Evaporation models often assume interaction with surrounding fields and particles. In chemically simple environments, interaction channels differ. This alters how theoretical evaporation rates are applied. JWST also constrains star formation histories in early systems. Reduced stellar feedback implies fewer energetic processes capable of disrupting compact objects. In such environments, black holes evolve in relative isolation. Isolation affects accretion, interaction, and potentially evaporation-related dynamics. While evaporation itself is intrinsic, the detectability of its consequences depends on surroundings. Importantly, JWST data highlight continuity rather than endpoints. Black hole-related phenomena appear across a range of epochs without abrupt transitions. This continuity supports models where black holes persist in various states rather than appearing and disappearing sharply. Complete evaporation predicts a clear absence below certain mass thresholds. JWST, instead, reveals a universe where black hole influence is persistent and widespread. The telescope also influences how theoretical confidence is weighted. Evaporation arguments are strongest where theory is clean and observation is absent. JWST narrows that gap. By showing that early universe black hole behavior differs from later analogues, it weakens the assumption that late-time physics extrapolates cleanly backward. Evaporation models derived from asymptotic conditions may not apply uniformly across cosmic history. JWST observations further complicate the use of indirect constraints. Many evaporation limits rely on assumptions about uniform distribution and isolation. Early universe conditions were neither uniform nor stable. Density variations, clustering, and dynamic backgrounds alter how black holes interact with space-time. These factors can modify evaporation outcomes without violating underlying theory. None of this constitutes direct evidence against Hawking evaporation. Rather, it demonstrates that the empirical context supporting complete evaporation is less secure than previously thought. JWST does not disprove evaporation. It reduces the confidence with which evaporation can be used to exclude entire classes of objects. This distinction matters. Cosmological exclusion requires high certainty. If black holes are used to explain dark matter, early structure formation, or seeding of supermassive objects, then evaporation must operate in a way that definitively eliminates those possibilities. JWST makes that elimination harder to justify without stronger empirical grounding. The telescope also shifts burden of proof. Previously, primordial black hole advocates were required to overcome evaporation objections. Now those objections must account for a universe where early black holes are common, environments are chemically simple, and observational silence is frequent. Theoretical certainty must match observational complexity. JWST thus acts as a stress test. It does not answer whether small black holes survive. It forces re-evaluation of how confidently their non-existence can be claimed. When foundational physics intersects with incomplete observation, conservative exclusion becomes inappropriate. This re-evaluation extends beyond black holes. It reflects a broader pattern in cosmology where early universe observations complicate late-time assumptions. Processes thought to be universal may depend on context in ways not previously recognized. In this sense, JWST challenges complete evaporation not through contradiction, but through displacement. It moves black hole physics into regimes where existing models operate with reduced authority. That displacement keeps primordial black holes within the space of viable explanations rather than closing it. The result is not resolution, but tension. Evaporation remains theoretically motivated, but its finality is uncertain. JWST amplifies that uncertainty by revealing a universe that does not conform neatly to simplified timelines or formation sequences. As observations push closer to the beginning, assumptions made at the end must be revisited. Hawking evaporation, once treated as a definitive endpoint, now sits within a framework of conditional outcomes. JWST ensures that those conditions are examined rather than assumed. This does not elevate primordial black holes to established fact. It preserves them as possibilities constrained by theory but not eliminated by observation. That preservation matters because it keeps open avenues for explaining phenomena that otherwise remain unresolved. JWST's role is therefore indirect but decisive. By altering expectations about black hole formation, abundance, and environment, it reshapes how evaporation arguments are applied. Complete evaporation remains possible, but no longer conclusive. In modern cosmology, that distinction is critical. Possibility and exclusion are separated by evidence, not assumption. JWST ensures that for now, evaporation-based exclusion of primordial black holes remains provisional rather than final. Primordial black holes as a dark matter candidate. Dark matter remains one of the most persistent unsolved problems in modern cosmology. Multiple independent observations indicate that visible matter accounts for only a small fraction of the universe's total mass. Galactic rotation curves, gravitational lensing, large-scale structure formation, and cosmic microwave background measurements all require an additional gravitational component that does not emit or absorb light. Despite decades of experimental effort, no particle-based dark matter candidate has been directly detected. This absence has kept alternative explanations under active consideration, including primordial black holes. Primordial black holes differ fundamentally from astrophysical black holes formed by stellar collapse. They are hypothesized to have formed directly from density fluctuations in the early universe, prior to star formation. Because they would be composed entirely of gravitational mass, they would interact with ordinary matter almost exclusively through gravity. This property places them within the operational definition of dark matter, regardless of their origin. The appeal of primordial black holes as dark matter candidates lies in their simplicity. They require no new particle physics beyond gravity and general relativity. If they exist in sufficient numbers and appropriate mass ranges, they could account for a portion, or potentially all of the missing mass inferred in galaxies and galaxy clusters. This possibility has been explored intermittently since the 1970s, often gaining renewed attention when particle-based searches produce null results. Constraints on primordial black holes as dark matter are strongly mass-dependent. Very massive black holes are ruled out as dominant dark matter components because their gravitational effects would disrupt stellar systems and produce detectable lensing signatures. Intermediate mass ranges are constrained by microlensing surveys, stellar heating, and dynamical friction effects. Extremely small black holes have been considered unlikely due to evaporation through Hawking radiation. What remains are narrow mass windows where primordial black holes are neither definitively excluded nor observationally confirmed. JWST observations influence this landscape indirectly by demonstrating that black holes appear earlier and in more diverse environments than previously expected. The telescope weakens arguments that rely on rarity. If black hole formation was efficient in the early universe, it becomes less speculative to consider that a non-negligible fraction of cosmic mass collapsed into compact objects outside the stellar pathway. One challenge for primordial black holes as dark matter is spatial distribution. Dark matter is inferred to form extended halos around galaxies, rather than concentrating exclusively at their centers. Primordial black holes would need to be sufficiently numerous and dynamically cold to reproduce this behavior. Simulations indicate that compact objects can form halos under certain initial conditions, though their clustering properties may differ from those of particle dark matter. JWST data contribute to this discussion by refining models of early structure formation. Observations of rapid galaxy assembly suggest that gravitational wells were established early, potentially aided by compact mass concentrations. While this does not require primordial black holes, it allows for their presence without contradiction. The early emergence of deep potential wells reduces tension between primordial black holes and observed large-scale structure. Another factor is interaction rate. Dark matter must be effectively collisionless on galactic scales. Primordial black holes satisfy this requirement if their number density is low enough to avoid frequent close encounters. In such regimes, their collective gravitational behavior can mimic that of a smooth dark matter fluid. JWST's ability to probe early galaxies without obvious signs of excessive dynamical heating supports the idea that compact objects, if present, are not causing large-scale instability. Radiative constraints remain important. Accretion onto primordial black holes could, in principle, produce detectable radiation, especially in the early universe. Excess heating or ionization would leave imprints on the cosmic microwave background. Existing measurements place limits on accretion efficiency. However, these limits depend on poorly constrained parameters such as gas density, angular momentum, and feedback processes. JWST observations of chemically primitive and low luminosity systems indicate that accretion environments can be inefficient, weakening some radiative constraints. Gravitational lensing surveys provide some of the strongest exclusions. Searches for microlensing events caused by compact objects passing in front of background stars have ruled out certain mass ranges as dominant dark matter components. Yet these surveys are sensitive to assumptions about velocity distributions and spatial uniformity. JWST observations suggest early galaxies may exhibit complex mass distributions, complicating straightforward extrapolation of local lensing constraints to cosmological scales. Another aspect is survivability. If a subset of primordial black holes avoided complete evaporation, they would persist as stable dark matter candidates. Recent theoretical work suggests that evaporation may slow dramatically near Planck-scale masses, potentially leaving long-lived remnants. JWST does not test this directly, but by preserving the plausibility of early black hole populations, it keeps remnant scenarios within consideration. Importantly, primordial black holes need not account for all dark matter to be relevant. Even a modest fraction could influence galaxy formation, seed supermassive black holes, or affect early star formation. JWST observations showing rapid black hole growth and early galactic maturity are consistent with scenarios where compact objects play a supporting rather than exclusive role. The question then is not whether primordial black holes are the dark matter, but whether they can be confidently excluded. JWST shifts this question toward uncertainty rather than resolution. The telescope does not confirm primordial black holes as dark matter, but it undermines arguments that rely on the improbability of their formation or survival. In cosmology, explanatory frameworks compete under incomplete information. Particle dark matter remains theoretically attractive, but its experimental absence leaves room for alternatives. Primordial black holes occupy a constrained but resilient niche within this space. JWST's findings enlarge that niche by demonstrating that the early universe behaved in ways that strain simplified formation models. As observational capabilities expand, dark matter candidates are increasingly evaluated on consistency rather than elegance. Primordial black holes remain consistent with many observations, including those refined by JWST. Their ultimate status depends on future constraints, not on assumptions inherited from earlier observational limits. In this context, JWST's most unsettling contribution may be methodological. It reminds cosmology that exclusion requires evidence, not expectation. Until primordial black holes are empirically ruled out across all viable mass ranges, they remain part of the dark matter conversation, not as a dominant solution, but as a persistent and unresolved possibility. Observational limits, and what JWST does not see. The absence of direct detection plays a central role in evaluating any cosmological hypothesis, and primordial black holes are no exception. Much of the skepticism surrounding their existence arises not from contradictory observations, but from the lack of positive evidence where signals were expected. Understanding what JWST does not observe is therefore as important as understanding what it does. Non-detections shape theoretical boundaries, but they also reflect instrumental limitations, environmental factors, and assumptions embedded in search strategies. Primordial black holes, particularly at small masses, are inherently difficult to observe. Unlike stellar or supermassive black holes, they are not expected to host luminous accretion disks under most conditions. Without surrounding gas or dust, they emit no light and interact with their environment only gravitationally. This makes them effectively invisible unless they produce secondary effects, such as lensing, radiation from accretion, or particle emission from evaporation. JWST does not detect isolated compact objects through gravity alone. Its instruments are sensitive to electromagnetic radiation, primarily in infrared wavelengths. As a result, JWST cannot directly image black holes unless they influence nearby matter in a way that produces detectable emission. This limitation is not unique to JWST, but applies to all electromagnetic observatories. Absence of detection, therefore, cannot be equated with absence of existence. One area where non-detection matters is accretion signatures. If primordial black holes were abundant and efficiently accreting gas, they would heat surrounding material and produce infrared or X-ray emission. JWST has observed many early galaxies with surprisingly low luminosity relative to their inferred mass. This has been interpreted as evidence of inefficient accretion or minimal energetic feedback. Such environments do not favor strong emission from compact objects, whether stellar or primordial. Another expected signature is gravitational lensing. Compact objects can bend light from background sources, producing transient brightening or image distortion. Microlensing surveys have searched extensively for these effects within the Milky Way and nearby galaxies. JWST is not optimized for wide-field, time-domain microlensing detection, and its deep-field observations are limited in temporal coverage. Consequently, its lack of microlensing detections provides no new constraints on small black hole populations. JWST also does not observe the high-energy radiation associated with black hole evaporation. Hawking radiation, if present, peaks at energies far outside JWST's detection range for small black holes. Even if evaporation were occurring, its products would be better sought with gamma-ray or particle detectors rather than infrared telescopes. Thus, JWST's silence on this front carries no evidentiary weight. Chemical and thermal signatures offer indirect constraints. Large populations of compact objects could alter gas temperatures, ionization states, or chemical pathways in early galaxies. JWST has measured gas composition and temperature in many primordial systems. These measurements show consistency with models of modest heating and gradual enrichment. However, these observations constrain only extreme scenarios. Subtle or rare compact object effects would remain undetectable. Spatial distribution is another factor. If primordial black holes cluster strongly, their effects could be localized and intermittent. JWST's snapshots of distant galaxies capture integrated properties rather than fine-grained mass distributions. Small-scale gravitational perturbations would be averaged out in such observations. The absence of large-scale disruption does not preclude the presence of smaller-scale compact mass components. JWST's strength lies in population-level inference rather than object-by-object identification. It reveals statistical patterns across galaxies and epochs. These patterns currently show no need to invoke primordial black holes, but they also do not exclude them. Cosmological models can accommodate JWST's findings with or without compact dark components, depending on parameter choices. Importantly, non-detection must be contextualized within prior expectations. Many exclusion arguments assume that primordial black holes would behave similarly to stellar black holes scaled down in mass. JWST observations of early galaxies suggest that black hole behavior depends strongly on environment. Low metallicity, low angular momentum, and sparse gas conditions reduce accretion efficiency and visibility. Applying late universe analogies to early universe objects may therefore be misleading. The telescope also reveals selection effects. JWST preferentially observes the brightest and most massive systems at high redshift. If primordial black holes exist primarily in faint or diffuse environments, they would fall below detection thresholds. Observational silence in biased samples cannot be generalized to the entire universe. Non-detection has historically been interpreted as falsification. In cosmology, this interpretation is increasingly viewed as overly rigid. The complexity of early universe physics and the limitations of current instruments require caution. JWST has already demonstrated that confident exclusions made prior to its launch were premature in other areas, including galaxy formation timelines and black hole growth rates. Thus, what JWST does not see cannot be reduced to a simple negative result. Its observations define boundaries of detectability rather than definitive absences. For primordial black holes, those boundaries remain broad. The practical consequence is uncertainty, not alarm. JWST neither confirms nor denies the existence of small primordial black holes. It highlights how little direct access exists to compact, non-luminous mass components. This lack of access preserves ambiguity rather than resolving it. In scientific terms, JWST has shifted the discussion from impossibility to constraint. Models invoking primordial black holes must fit within increasingly detailed observations, but they are not eliminated by them. Conversely, models excluding such objects must explain why early universe behavior remains compatible with their absence. JWST's most important contribution here is restraint. It demonstrates that even transformative instruments leave fundamental questions unanswered. Observational limits remain part of the landscape, shaping but not closing theoretical space. For primordial black holes, silence continues, and silence alone does not constitute disproof. Theoretical responses to JWST's constraints. As observational data from the James Webb Space Telescope continues to accumulate, theoretical models addressing early universe black holes have undergone significant revision. These adjustments are not reactions to a single discovery, but responses to a pattern. JWST has altered timelines, environments, and boundary conditions in ways that force theorists to revisit assumptions that once appeared stable. The result is not consensus, but diversification of theoretical approaches. One major response has been the refinement of formation models. Early primordial black hole theories often assumed simple density thresholds in an otherwise smooth early universe. JWST data support a more complex picture. The early universe appears structured sooner than expected, with rapid assembly of galaxies and mass concentrations. This has motivated models that incorporate non-Gaussian density fluctuations, phase transitions, and enhanced curvature perturbations during inflation. These mechanisms allow compact objects to form over a wider mass range without requiring extreme fine-tuning. Another area of revision concerns mass spectra. Earlier models tended to favor narrow mass windows for primordial black hole formation to satisfy observational constraints. JWST-driven revisions increasingly explore extended mass functions. If black holes formed across many scales simultaneously, then observational limits excluding one mass range do not eliminate the entire population. Extended spectra also allow small populations to survive in observationally quiet regimes, consistent with JWST's findings of low luminosity systems. Accretion modeling has also evolved. Traditional accretion prescriptions assumed spherically symmetric gas inflow and steady-state conditions. JWST observations of chaotic, clumpy, and metal-poor environments suggest these assumptions are often invalid in early galaxies. New models incorporate angular momentum barriers, radiative inefficiencies, and intermittent accretion. These refinements reduce predicted luminosities and weaken constraints based on expected radiation output. Theoretical work on evaporation has similarly adjusted. While Hawking radiation remains foundational, recent models explore scenarios where evaporation slows near quantum gravity scales. JWST does not test these models directly, but its preservation of early black hole plausibility incentivizes their development. Theoretical interest has shifted from whether evaporation occurs to how it proceeds under realistic early universe conditions. Dark matter modeling has also been affected. Particle-based models now increasingly coexist with hybrid frameworks in which dark matter consists of multiple components. In such models, primordial black holes contribute a fraction of total dark matter without dominating it. JWST's observations of early structure formation accommodate this possibility, as compact objects can influence gravitational dynamics without overwhelming them. Feedback processes represent another focus. JWST has shown that energetic feedback in early galaxies does not always suppress structure formation as strongly as expected. This has encouraged theoretical treatments where black hole feedback operates episodically or anisotropically. Such feedback would alter local environments without erasing large-scale features. These models align with observations of early galaxies that appear massive, yet relatively undisturbed. Simulations have become more granular in response. High-resolution numerical models now track compact objects within evolving cosmic environments rather than treating them as isolated entities. JWST provides calibration points for these simulations by constraining star formation rates, gas distributions, and metallicities at early epochs. Theoretical models must now reproduce these properties while remaining consistent with black hole physics. Another shift involves probabilistic reasoning. Rather than asking whether primordial black holes exist, many models now quantify likelihoods under varying assumptions. JWST's data reduces uncertainty in some parameters while increasing it in others. Theoretical work reflects this by mapping regions of parameter space that remain viable, rather than claiming definitive outcomes. Importantly, theoretical responses emphasize compatibility rather than prediction. JWST has demonstrated that confident predictions about the early universe are risky. Models are increasingly judged by their ability to remain consistent with a wide range of observations rather than by their explanatory completeness. This favors flexible frameworks that accommodate primordial black holes without requiring them. The role of falsifiability has also been reconsidered. In principle, primordial black hole models are testable. In practice, JWST shows that tests are indirect and conditional. Theoretical work now often focuses on identifying unique signatures that would distinguish compact object scenarios from particle-based alternatives. These include subtle lensing effects, gravitational wave backgrounds, and correlations between black hole presence and early galaxy morphology. Interdisciplinary influence is evident as well. Developments in quantum gravity, inflationary theory, and high-energy physics increasingly inform cosmological black hole models. JWST's data encourages cross-field collaboration by exposing where astrophysical observation intersects with fundamental physics. Theoretical responses therefore extend beyond cosmology into broader physical theory. Despite diversification, constraints remain real. JWST does not relax all limits. It tightens some by confirming early chemical simplicity, modest feedback, and specific star formation histories. Theoretical models must fit within these constraints or be discarded. The space of viable ideas is reshaped, not expanded indiscriminately. What emerges is a landscape of cautious adaptation. JWST has not validated primordial black holes, but it has altered the criteria by which they are evaluated. Theoretical certainty has been replaced by conditional plausibility. Models survive not by asserting dominance, but by remaining consistent under revision. This response reflects a broader shift in cosmology. As observations approach the limits of cosmic history, theory becomes less declarative and more adaptive. JWST accelerates this trend by revealing complexity where simplicity was assumed. The question is no longer whether primordial black holes violate known physics, but whether existing physics adequately captures early universe conditions. JWST suggests it may not, and theoretical responses increasingly acknowledge that possibility. Potential risks versus physical reality. Discussions involving primordial black holes often drift toward risk, despite the absence of evidence for immediate threat. This tendency reflects how unfamiliar phenomena are interpreted rather than what physics indicates. Evaluating risk requires separating speculative scenarios from mechanisms that are physically plausible. JWST's role in this evaluation is indirect, but it sharpens the distinction by grounding discussion in observable conditions rather than abstract possibility. Primordial black holes, if they exist today, would be compact objects interacting almost exclusively through gravity. For small masses, their gravitational influence would be highly localized. A black hole with the mass of a mountain or even an asteroid would exert no noticeable force beyond microscopic distances. At scales relevant to planets, stars, or spacecraft, Such an object would be dynamically insignificant unless encountered at extremely close range. Collision probabilities are therefore central to risk assessment. Space is vast, and even if primordial black holes were numerous, their number density would be extraordinarily low. The probability of a direct encounter with a microscopic compact object is orders of magnitude smaller than many accepted cosmic risks. Asteroid impacts, stellar flares, and cosmic radiation present far greater known hazards, yet are managed through observation and mitigation rather than alarm. Gravitational effects scale with mass. Small primordial black holes cannot consume matter in the way often imagined. Accretion requires interaction cross-sections far larger than such objects possess. Without extended atmospheres or accretion disks, they do not grow through casual encounters. Matter passing nearby would experience a brief deflection rather than capture. The idea of a small black hole acting as a roaming destructive agent conflicts with established gravitational dynamics. Evaporation further reduces risk in many scenarios. If Hawking radiation proceeds as traditionally described, smaller black holes lose mass over time rather than gain it. Even in remnant models where evaporation slows or halts, the end state involves stable, inert objects rather than active consumers of matter. JWST does not alter this fundamental behavior. Radiation hazards are also constrained. Hawking radiation from very small black holes would be intense only near the final stages of evaporation. If such events occurred nearby, they would be transient and detectable. No evidence of such signatures exists within observational limits. JWST does not observe high-energy backgrounds consistent with widespread evaporation events. Concerns about navigation or exploration hazards arise from misunderstanding scale. A microscopic black hole does not present a region of extended danger. Its effective gravitational reach is negligible. Even hypothetical spacecraft encounters would require improbably precise alignment. The same applies to natural systems. Planets and stars are not at risk from unseen compact objects passing through space. JWST's observations reinforce this perspective by showing that early universe black holes, even massive ones, coexist with structured environments without destabilizing them. If compact objects posed intrinsic danger through passive presence, early galaxies would exhibit widespread disruption. Instead, JWST reveals organized star formation, stable disks, and coherent dynamics across cosmic time. The most substantial risks associated with black holes arise from supermassive systems with active accretion and energetic feedback. These systems influence galaxy evolution, but they operate over millions of years and vast distances. JWST has expanded understanding of such processes without identifying new categories of threat. Risk perception often escalates when phenomena lack direct sensory analogues. Primordial black holes fall into this category. Their invisibility encourages imaginative extrapolation. Scientific evaluation counters this by quantifying interactions rather than narrating scenarios. When quantified, risks diminish sharply. From a planetary perspective, Earth has existed for billions of years within a galaxy shaped by countless gravitational interactions. If primordial black holes existed in significant numbers, Earth has already survived their presence. JWST's contribution is to show that the universe's early behavior was more complex than expected, not more hostile. The distinction between theoretical possibility and physical relevance is essential. Many phenomena are permitted by equations without posing meaningful risk. Primordial black holes, if real, belong to this category. Their importance lies in cosmology and fundamental physics, not hazard. JWST shifts the conversation by emphasizing evidence over imagination. It provides data that constrain environments and interactions. Within those constraints, catastrophic scenarios lack support. This does not trivialize uncertainty, it contextualizes it. Unknowns remain about early universe processes, but unknown does not equate to dangerous. Scientific caution applies to interpretation, not fear. Ultimately, potential risk from primordial black holes is negligible compared to known cosmic processes. JWST reinforces this by grounding black hole discussion in observed structure rather than speculative extremes. The persistence of alarmist narratives reflects human psychology more than astrophysics. JWST's findings invite a recalibration toward proportionality. Curiosity replaces concern, and investigation replaces conjecture. In this framework, the question becomes not whether primordial black holes threaten existence, but whether they inform understanding. JWST suggests that if they exist, their role is explanatory rather than destructive. Risk, properly evaluated, recedes. What remains is a scientific problem defined by observation, theory, and uncertainty, not danger. Why JWST has reopened questions thought settled. For much of modern cosmology, several questions surrounding the early universe were treated as effectively resolved. While uncertainty remained at the margins, the core frameworks appeared stable enough to justify exclusion of alternative scenarios. Primordial black holes fell into this category. They were not disproven through direct observation, but through a layered structure of assumptions that rendered them unnecessary. The James Webb Space Telescope has disrupted that structure, not by contradicting specific results, but by revealing how dependent those results were on contextual expectations that no longer hold. The most significant shift introduced by JWST concerns chronology. Prior to its launch, black hole formation models assumed a relatively orderly progression. Stars formed first, stellar remnants followed, and black holes grew gradually through accretion and mergers. This sequence imposed strict limits on what kinds of objects could plausibly exist at early epochs. JWST has shown that massive black holes appear far earlier than anticipated. Once this timeline changes, many downstream assumptions weaken simultaneously. Early appearance alone does not prove primordial origins. Alternative explanations exist, including rapid accretion and direct collapse pathways. However, these explanations often require finely tuned conditions or sustained growth rates near theoretical limits. When models depend on extreme efficiency rather than direct evidence, confidence declines. JWST therefore reopens alternatives not because they are demonstrated, but because dominant explanations are strained. Environmental maturity represents a second disrupted assumption. Early galaxies were expected to be chaotic, highly energetic, and chemically active. JWST, instead, reveals systems that are organized, chemically primitive, and relatively stable. These environments differ substantially from those used to derive many observational constraints. Black hole formation, growth, and visibility depend strongly on surrounding conditions. Constraints derived from later, metal-rich, high-feedback environments cannot be applied unchanged to these early systems. JWST has also highlighted the role of observational bias. Many conclusions about what does not exist were drawn from what earlier telescopes could not see. JWST demonstrates that invisibility often reflects instrumental limitation rather than absence. Objects previously thought too rare or faint to matter now appear common when observed with sufficient sensitivity. This lesson extends beyond galaxies and applies equally to compact mass components. Another factor is theoretical completeness. Cosmological models often prioritize parsimony, favoring minimal assumptions when multiple explanations are possible. When particle dark matter candidates appeared promising, alternatives such as primordial black holes were deprioritized. JWST does not invalidate particle models, but it weakens the argument that simplicity guarantees correctness. The early universe appears capable of producing outcomes that are not minimal, but emergent. Scale also plays a critical role. JWST probes epochs close to cosmic dawn, where physical conditions differ fundamentally from later times. At these scales, approximations commonly used in cosmology lose reliability. Assumptions about homogeneity, equilibrium, and gradual evolution become less secure. When foundational approximations weaken, conclusions derived from them must be revisited. Exclusion logic is particularly affected. Many arguments against primordial black holes rely on cumulative reasoning, combining constraints from evaporation, lensing, dynamics, and background radiation. Each component carries uncertainty. JWST has increased uncertainty in several components simultaneously by altering timelines, environments, and formation efficiency estimates. When multiple uncertainties align, exclusion becomes provisional rather than definitive. Importantly, JWST does not reopen questions by presenting contradictory evidence. It does so by expanding the range of scenarios that remain observationally consistent. This expansion is subtle but significant. Possibility persists where certainty was previously assumed. The reopening is therefore methodological rather than evidentiary. JWST reminds cosmology that absence of evidence is conditional on observational reach. As reach expands, conclusions must be reassessed. This does not imply that earlier work was flawed, only that it was limited by available data. Another driver is accumulated surprise. JWST has repeatedly revealed systems that violate expectations without violating physical laws. Each surprise reduces confidence in assumptions that have not been directly tested. Primordial black holes benefit from this erosion not because they are supported, but because exclusion arguments lose authority. The distinction between speculative and implausible also shifts. Ideas once considered speculative due to lack of motivation gain relevance when dominant narratives encounter difficulty. JWST has created such difficulty by revealing early universe behavior that resists simplified explanation. In that context, primordial black holes re-enter discussion as unresolved possibilities rather than fringe concepts. This reopening reflects the iterative nature of scientific progress. Conclusions are conditional statements bounded by data quality and scope. JWST has altered both. Questions thought settled were settled relative to earlier instruments, not absolute truth. Crucially, JWST demonstrates that early universe behavior cannot be inferred reliably from late universe analogues. Many exclusions relied on that inference. Once it weakens, the exclusions weaken with it. What emerges is not reversal, but suspension. Primordial black holes are neither confirmed nor dismissed. They occupy a space reopened by improved observation and reduced reliance on extrapolation. JWST's role is catalytic rather than decisive. It does not advocate for specific alternatives. It undermines the confidence that alternatives were unnecessary. This distinction matters because cosmology advances by eliminating assumptions before eliminating possibilities. As JWST continues observing, some reopened questions may close again under stronger constraints. Others may fragment into new sub-questions. This reflects maturation rather than regression. In this sense, JWST's most consequential impact is structural. It demonstrates that cosmology progresses not by freezing answers in place, but by revisiting them as observational capability improves. Questions thought settled were settled within boundaries that JWST has now exposed. What remains open is not a failure of theory, but an opportunity to refine it under conditions closer to cosmic origin. This reopening is not unsettling from a scientific standpoint. It is expected. Precision replaces confidence, and uncertainty is acknowledged rather than avoided. JWST has therefore not made the universe more mysterious. It has made cosmological reasoning more honest. By reopening questions thought resolved, it reinforces the principle that closure in science is always provisional, bounded by what can be observed rather than what is assumed. What would confirm or refute this scenario? In cosmology, hypotheses persist only as long as they remain testable in principle. Primordial black holes fall squarely into this category. They are neither beyond empirical reach nor easily verified. Clarifying what would actually confirm or refute their existence explains why the question remains unresolved and why the James Webb Space Telescope influences the discussion indirectly rather than decisively. Confirmation would require evidence that cannot be explained by conventional astrophysical processes or particle-based dark matter models. Specifically, it would require demonstrating the existence of compact mass objects that formed independently of stars and stellar remnants. Any confirming signal must therefore distinguish between black holes created through stellar collapse and those originating from early universe density fluctuations. Gravitational lensing provides one of the most direct potential confirmation pathways. Compact objects passing in front of background stars or galaxies can produce measurable lensing effects. For primordial black holes, confirmation would involve detecting lensing events that cannot be attributed to known stellar populations, planets, or brown dwarfs. This requires statistically significant excesses across well-defined mass ranges, combined with spatial and velocity distributions inconsistent with baryonic matter. Such confirmation would need to occur across multiple surveys and environments. Isolated detections would be insufficient. Consistency across independent datasets would be required to rule out observational bias or misclassification. Importantly, lensing confirmation would not rely on imaging black holes directly, but on gravitational effects that are mass-dependent and insensitive to composition. Gravitational wave observations offer another potential route. Black hole mergers encode information about progenitor masses and formation history. Detection of mergers involving black holes with masses below known stellar formation thresholds, especially at high redshift, would strongly favor primordial origins. Confirmation would require merger rates and mass distributions that cannot be produced by stellar evolution, even under extreme assumptions. The redshift distribution of such mergers would be critical. Primordial black hole mergers would be expected to occur earlier and more uniformly than stellar origin mergers, which track star formation history. Distinguishing these populations statistically would require large datasets from next-generation gravitational wave observatories. Cosmic microwave background measurements provide another test. Accretion onto compact objects in the early universe would inject energy into surrounding plasma, altering ionization histories and temperature anisotropies. Improved precision in CMB observations could reveal subtle deviations consistent with compact object populations. Confirmation would require patterns that cannot be reproduced by particle dark matter or standard astrophysical feedback. Evaporation signatures represent a more direct but challenging test. Detection of high-energy radiation consistent with late-stage Hawking evaporation would strongly support the existence of small black holes. Such events would be rare and transient, requiring sensitive gamma-ray or particle detectors capable of distinguishing them from other high-energy astrophysical phenomena. Importantly, confirmation depends on understanding evaporation behavior, which remains theoretically uncertain. Chemical and structural signatures may also contribute indirectly. If compact objects influenced early star formation or gas dynamics, they could leave subtle imprints on galaxy morphology, clustering, or chemical enrichment patterns. Confirmation would require identifying correlations that cannot be explained by conventional feedback mechanisms, mergers, or environmental variation. Refutation, by contrast, is significantly more demanding. Demonstrating that primordial black holes do not exist would require comprehensive exclusion across all viable mass ranges and formation scenarios. This includes not only dominant dark matter contributions, but also subdominant populations. Partial exclusion is insufficient if claims of impossibility are made. Refutation depends critically on confidence in underlying physics. Complete evaporation through Hawking radiation would eliminate small primordial black holes, only if evaporation behavior is fully understood down to quantum gravity scales. Current theory does not meet this standard. Any refutation based on evaporation, therefore, remains conditional. Similarly, lensing and dynamical constraints rely on assumptions about spatial distribution, clustering, and velocity dispersion. If primordial black holes cluster differently from baryonic matter or exist primarily in low-density regions, some constraints weaken. Refutation requires these assumptions to be robust across cosmic environments. JWST contributes to this evaluation by refining early universe conditions. It does not confirm primordial black holes, but it informs which tests are meaningful and which assumptions require caution. By clarifying star formation histories, chemical environments, and galaxy assembly timelines, JWST helps define where confirmation signals should appear and where refutation claims may be overstated. Future instruments will be decisive. Wide-field time domain surveys will improve microlensing statistics. Next-generation gravitational wave detectors will expand sensitivity to lower masses and higher redshifts. High-energy observatories will refine evaporation searches. Confirmation or refutation therefore remains deferred rather than denied. It is also important to distinguish falsification from irrelevance. Even if primordial black holes cannot account for all dark matter, their existence would remain scientifically significant. Refutation must therefore address even minor populations if claims of non-existence are made. The distinction between absence of evidence and evidence of absence remains central. JWST reinforces this distinction by showing how observational limits shape conclusions. Objects can exist below detection thresholds without contradicting current data. Ultimately, primordial black holes will be confirmed or excluded through convergence of multiple independent lines of evidence. No single observation will suffice. Confirmation requires consistency across gravitational, electromagnetic, and cosmological probes. Refutation requires closing every viable theoretical loophole. Until that convergence occurs, the scenario remains conditional. JWST does not decide the outcome, but it reshapes the criteria by which decisions will be made. It narrows some pathways and widens others. In scientific practice, hypotheses fade only when tests close decisively. For primordial black holes, those tests remain open. JWST ensures that they remain grounded in observation rather than assumption, preserving the question as an empirical one rather than a settled matter. Implications for cosmology if the scenario is correct. If primordial black holes exist in non-negligible numbers today, the implications for cosmology would extend well beyond a single unresolved hypothesis. Their presence would affect how matter assembled, how early structures evolved, and how foundational assumptions about the universe's first moments are interpreted. The impact would not be dramatic in the sense of sudden upheaval, but structural, altering models gradually, yet fundamentally, across multiple domains of cosmology. The first major implication concerns the initial conditions of the universe. Primordial black holes would indicate that density fluctuations in the early universe were capable of collapsing on very small scales. This would provide direct evidence that inflationary processes produced features beyond smooth, nearly Gaussian perturbations. Several inflationary models predict enhanced curvature fluctuations, phase transitions, or brief departures from uniform expansion. Primordial black holes would act as preserved records of these processes, offering insight into physics otherwise inaccessible. Structure formation models would also require revision. In standard cosmology, dark matter seeds structure through gradual gravitational amplification, with smooth halos forming first and baryonic matter following. Compact objects introduce discreteness into this picture. Even if primordial black holes represented only a fraction of total dark matter, their localized gravity could accelerate early halo formation. This effect could help explain why galaxies appear organized and massive earlier than expected without invoking extreme assumptions about star formation efficiency. Galaxy assembly timelines would need recalibration. JWST observations already show galaxies forming rapidly. If compact objects were present, embedded within dark matter halos, they could deepen gravitational potentials early on. Deeper potentials would draw gas inward more efficiently, supporting faster disk formation and earlier stabilization. This mechanism would not replace existing explanations, but would operate alongside them, contributing incrementally over cosmic time. Black hole seeding models would shift substantially. If some black holes formed primordially, then stellar collapse would no longer be the sole pathway. Growth histories inferred from accretion rates, luminosities, and feedback would need reinterpretation. Some supermassive black holes might originate from massive seeds rather than prolonged growth from stellar remnants. This would alter inferred duty cycles and reduce tension between observed masses and available growth time. Chemical evolution would be affected indirectly. The timing and distribution of star formation influences how and when heavy elements appear. Compact objects affecting gravitational potentials could change where stars form first and how quickly enrichment proceeds. This could help reconcile observations of chemically primitive galaxies hosting massive black holes without requiring suppressed star formation across entire systems. Dark matter theory would become more pluralistic. Particle candidates would not be eliminated, but compact objects would represent an additional component. Cosmological models would incorporate mixed dark matter scenarios, complicating parameter estimation, but potentially resolving tensions between small-scale and large-scale observations. This would mark a shift away from single-solution frameworks toward layered explanations. Constraints derived from smooth dark matter assumptions would require revision. Many simulations treat dark matter as a continuous fluid. Introducing discrete masses alters microdynamics, particularly at early times. While large-scale behavior might remain similar, small-scale predictions such as core formation, satellite distributions, and early halo mergers would change. These differences would provide new observational tests. Gravitational wave astronomy would gain new relevance. Mergers between primordial black holes would produce signals with mass distributions and redshift patterns distinct from stellar origin events. Even rare mergers would contribute to a stochastic background. Population statistics would become probes of early universe physics rather than purely astrophysical processes. Evaporation physics would also become empirically important. If small black holes survive, theories of quantum gravity would face observational pressure. The final stages of black hole evaporation would no longer be academic. This would motivate new theoretical work linking cosmology with fundamental physics and potentially guide experimental efforts toward relevant energy scales. Cosmic history narratives would adjust. The early universe would be seen less as a smooth progression from simplicity to complexity, and more as a landscape where compact, high-density objects emerged alongside diffuse matter. This reframing emphasizes heterogeneity rather than uniformity, suggesting that structure emerged through multiple parallel processes rather than a single dominant pathway. Importantly, these implications do not require a catastrophic rewrite of cosmology. Existing models would not collapse. They would be extended. Primordial black holes would join neutrinos, baryons, and particles as contributors to cosmic structure, integrated rather than disruptive. JWST's role in this hypothetical future would be historical. It would be recognized as the instrument that reopened critical questions at a decisive moment, preventing premature closure. Its observations would serve as boundary conditions, shaping theory rather than proofs settling it. The broader lesson would concern scientific humility. Cosmology would be reminded that exclusion based on convenience can delay understanding. Allowing multiple possibilities to coexist until evidence resolves them leads to more resilient theory and fewer forced explanations. If the scenario is correct, it would not mean previous work was wrong. It would mean it was incomplete. Models evolve as data improves. Primordial black holes would exemplify how progress often comes through expansion rather than replacement. The most significant implication would be methodological. Future claims of impossibility would be treated with caution, especially when rooted in untested regimes. JWST has already encouraged this caution by repeatedly revealing early universe behavior that strains simplified assumptions. In practical terms, cosmology would become more interconnected. Inflation, quantum gravity, dark matter, and galaxy formation would converge around shared questions rather than isolated domains. Observations would increasingly test multiple theories simultaneously. The universe described by such a model would not be more threatening or exotic. It would be more textured. Complexity would replace oversimplification, and uncertainty would be acknowledged rather than suppressed. Whether or not primordial black holes exist, JWST has demonstrated that early universe physics retains surprises. If they do exist, they would represent one such surprise, integrated quietly into the structure of reality rather than announced dramatically. The scenario's correctness would therefore matter not for fear, but for understanding. It would reshape cosmology by adding depth rather than disorder, altering frameworks without overturning foundations. In that sense, the implications would be profound but restrained, advancing knowledge through refinement rather than disruption, and reinforcing the idea that the universe often resists the simplest explanations we prefer to give it. Why this discovery feels unsettling without being dangerous. The reaction to recent interpretations of James Webb Space Telescope data has revealed an important distinction in how scientific information is processed. Certain findings generate discomfort without implying threat. The discussion surrounding early black holes and the possible survival of primordial compact objects falls into this category. The unease does not arise from danger, but from implication. It reflects tension between expectation and evidence, rather than between safety and risk. For decades, cosmology relied on a broadly coherent narrative of cosmic evolution. Matter condensed gradually, stars formed first, and black holes emerged as endpoints of stellar life cycles. This narrative provided not only explanatory power, but psychological closure. It suggested an orderly universe governed by well-understood sequences. JWST has not invalidated this narrative, but it has complicated it. Complexity, rather than contradiction, is what unsettles. The unsettling aspect stems from scale and timing. When massive black holes appear earlier than expected, it challenges the assumption that extreme outcomes require long processes. This does not introduce danger, but it undermines the comfort of gradualism. Humans tend to associate slow processes with control and predictability. Rapid emergence implies that certain outcomes are less constrained by time than previously believed. Another source of unease is invisibility. Compact objects that interact only through gravity defy intuitive detection. When phenomena cannot be seen directly, they are often perceived as more threatening than they are. In reality, invisibility in physics usually corresponds to weak interaction, not hidden power. Primordial black holes, if present, would be among the least interactive objects conceivable. JWST reinforces this paradox. It reveals unseen mass influencing visible structure without dramatic effects. Galaxies remain stable, stars form coherently, and large-scale order persists. The unsettling element is not disruption, but coexistence. The universe accommodates these possibilities without exhibiting instability. Uncertainty itself plays a role. Scientific uncertainty is often misinterpreted as hazard. In cosmology, uncertainty usually reflects limits of observation rather than unpredictability of behavior. The laws governing gravity remain unchanged. What changes is confidence in which configurations those laws permit. That shift affects explanation, not safety. The term terrifying often appears in public discourse surrounding such discoveries. This framing reflects emotional response rather than scientific assessment. From a physical standpoint, primordial black holes introduce no new mechanisms of harm. Their gravitational influence is bounded by mass, and small masses produce negligible effects beyond microscopic scales. JWST's data further reduce grounds for fear by demonstrating environmental compatibility. Early galaxies hosting massive black holes show no signs of catastrophic instability. Star formation proceeds, disks persist, and chemical evolution unfolds. If black holes posed inherent danger through mere presence, these systems would exhibit disruption. They do not. The discomfort instead arises from epistemology. Cosmology has long depended on exclusion to simplify complexity. When exclusions weaken, complexity returns. This feels unsettling because it requires holding multiple possibilities simultaneously. Human cognition prefers resolution. Science often resists it. Another factor is narrative expectation. Black holes occupy a unique place in cultural imagination. They are associated with destruction, consumption, and finality. Scientific descriptions emphasize gravity and geometry, but cultural associations persist. When JWST revives discussion of black holes outside familiar categories, those associations resurface despite lack of physical justification. Importantly, JWST does not introduce unknown forces or behaviors. It reveals that known forces operated under conditions we had not fully characterized. This distinction matters. Unknown forces would imply new risks. Known forces operating differently imply new understanding. The absence of immediacy is also key. Even if primordial black holes exist, their effects unfold over cosmological timescales. Human-scale consequences are effectively non-existent. The universe has operated under these conditions for billions of years without interruption to planetary systems. JWST's role in unsettling perception is therefore indirect. It acts as a mirror reflecting the limits of certainty rather than a harbinger of threat. The discomfort signals adjustment rather than alarm. Scientific progress often follows this pattern. Discoveries that expand possibility space initially feel destabilizing. Over time, they are integrated into revised frameworks and lose their emotional charge. The heliocentric model, deep time, and cosmic expansion all followed similar trajectories. The distinction between danger and discomfort is crucial. Danger implies physical harm. Discomfort implies conceptual revision. JWST contributes to the latter. It challenges assumptions about formation efficiency, timing, and completeness without altering physical laws governing stability. Even speculative extensions, such as primordial black holes contributing to dark matter, do not introduce hazardous scenarios. Dark matter already permeates galaxies without destructive interaction. Replacing some fraction of it with compact objects does not alter that fundamental behavior. The feeling of unease also reflects loss of narrative dominance. When a single explanation no longer suffices, authority becomes distributed among competing models. This pluralism feels unstable, but is a normal stage in scientific development. JWST's findings do not imply that something was missed that should have been feared. They imply that something was simplified for practical reasons and must now be revisited. This revision affects explanation, not outcome. In practical terms, the universe revealed by JWST remains consistent with long-term stability. Stellar lifetimes, galactic dynamics, and cosmic expansion proceed as before. The unsettling element lies in interpretation rather than operation. As understanding deepens, this discomfort will likely recede. Revised models will absorb new data, and uncertainty will narrow. What feels unsettling now will become routine knowledge. In this sense, the emotional response says more about human expectations than about cosmic behavior. JWST has not revealed a hostile universe. It has revealed a nuanced one. The proper response is not fear, but recalibration. Scientific frameworks adapt. Emotional framing lags behind. Ultimately, the discoveries feel unsettling because they challenge intellectual comfort zones, not because they threaten physical reality. The universe remains indifferent to human concern, governed by consistent laws that JWST continues to illuminate rather than overturn. What JWST has done is reopen inquiry, not introduce peril. The distinction is essential. This distinction matters because cosmology operates at the boundary between what can be observed and what must be inferred. JWST pushes that boundary outward, revealing that prior certainty often rested on incomplete visibility rather than settled physics. When visibility improves, inference must adjust. That adjustment can feel destabilizing even when it leads to more accurate understanding. The unease therefore reflects transition. Old explanatory shortcuts are no longer sufficient, but new ones are still forming. JWST occupies this transitional moment. where clarity increases even as certainty temporarily decreases. Such moments are common in scientific advancement and are typically followed by consolidation rather than chaos. How this fits into the broader history of black hole research. The current discussion surrounding early black holes and the implications raised by James Webb Space Telescope observations does not exist in isolation. It fits into a longer history of black hole research marked by repeated cycles of prediction, skepticism, observational limitation, and eventual revision. Understanding this history clarifies why the present moment feels significant without representing a rupture from established scientific practice. Black holes entered scientific theory through mathematics rather than observation. Solutions to Einstein's field equations in the early 20th century implied the existence of regions where gravity became so strong that escape was impossible. These solutions were initially treated as curiosities rather than physical objects. For decades, black holes were considered artifacts of idealized equations rather than entities likely to exist in nature. The first shift occurred when astronomers began detecting compact objects exerting extreme gravitational influence. X-ray binaries and stellar remnants suggested the presence of collapsed objects too massive to be neutron stars. Even then, the term black hole was resisted, reflecting discomfort with objects that defied direct observation. Acceptance followed evidence slowly, not through a single discovery, but through accumulation. A second major shift came with the discovery of quasars and active galactic nuclei. These objects exhibited luminosities far exceeding what could be produced by stars alone. The only viable explanation involved accretion onto extremely massive compact objects. Supermassive black holes transitioned from theoretical speculation to practical necessity. Again, acceptance followed necessity rather than preference. Each stage of black hole research involved redefinition of limits. Objects once thought impossible became required to explain observation. Each time, resistance stemmed less from evidence and more from discomfort with implication. Black holes forced revisions of intuition about space, time, and matter. The emergence of stellar mass black holes further normalized the concept. Observations of gravitational waves from merging black holes confirmed predictions with precision. By the early 21st century, black holes were no longer exotic exceptions, but integral components of astrophysical models. Primordial black holes occupy a similar position today. They are not required by current observations, but neither are they excluded by them. Historically, this intermediate status has often preceded re-evaluation rather than dismissal. Black hole research repeatedly demonstrates that absence of requirement is not equivalent to impossibility. The James Webb Space Telescope represents another observational expansion comparable to earlier milestones. Like X-ray astronomy and gravitational wave detection, it opens regimes previously inaccessible. Each expansion has historically exposed limitations in existing models, rather than confirming them unchanged. Early black hole research relied heavily on analogies to known stellar processes. JWST disrupts this reliance by revealing conditions unlike those observed locally. This mirrors earlier moments when analogies failed. Quasars could not be understood as scaled-up stars, and supermassive black holes could not be treated as simple aggregates of stellar remnants. The present discussion reflects continuity rather than novelty. Cosmology regularly revisits assumptions when new instruments reveal regimes where those assumptions were untested. Black holes have repeatedly served as catalysts for such revision because they sit at the intersection of gravity, quantum theory, and observation. Another historical parallel concerns resistance rooted in methodological comfort. Simplified models are favored when observational constraints are weak. As data improves, complexity returns. Black hole research repeatedly follows this pattern. JWST's impact aligns with this trajectory. Importantly, black hole history shows that acceptance does not follow dramatic announcement. It follows gradual adjustment. Supermassive black holes were debated for decades before consensus formed. Primordial black holes may follow a similar path, remaining provisional until converging evidence accumulates. The current moment also reflects improved caution. Earlier eras sometimes overstated certainty based on limited data. JWST's influence encourages restraint, emphasizing boundaries rather than conclusions. This reflects maturation of the field rather than indecision. In historical context, JWST does not introduce a fundamentally new category of uncertainty. It exposes existing uncertainty that had been obscured by observational limitation. Black hole research has repeatedly advanced by acknowledging such exposure rather than resisting it. The broader lesson is that black hole science progresses through confrontation with extremes. Each time instruments reach further, theory adjusts. JWST extends that reach to cosmic dawn, where extremes of density, temperature and timescale converge. Viewed historically, the current debate fits a familiar pattern. A class of objects exists within theory, lacks decisive evidence, and remains constrained but unresolved. Over time, either constraints tighten decisively or evidence accumulates. JWST accelerates this process without predetermining its outcome. This perspective reduces the sense of anomaly. The present discussion is not an aberration, but a continuation. Black holes have consistently challenged cosmology by exposing where extrapolation fails. JWST continues this tradition. The broader history also emphasizes patience. Black hole acceptance has never been immediate. Each stage required multiple observational advances. JWST represents one such advance, not a final one. Understanding this context reframes the current moment. It is neither revolutionary nor trivial. It occupies the middle ground where evidence reshapes confidence without delivering closure. In that sense, JWST's contribution fits squarely within the established rhythm of black hole research. It opens questions, refines constraints, and postpones certainty until observation catches up with theory. What distinguishes the present era is not the uncertainty itself, but the precision with which uncertainty is now identified. Earlier debates often suffered from ambiguity about whether gaps reflected missing physics or missing data. JWST reduces that ambiguity by clearly showing where data ends and inference begins. This clarity does not resolve debate, but it structures it. As a result, contemporary black hole research is less about defending positions and more about mapping limits. The historical arc bends away from categorical claims and toward conditional understanding. JWST sits at this inflection point, reinforcing a long-standing pattern in black hole science where deeper observation leads not to closure, but to more carefully defined questions. What comes next for JWST and black hole investigation? The questions raised by James Webb Space Telescope observations are not endpoints. They define the beginning of a longer investigative phase rather than a conclusion. JWST was never intended to deliver final answers about black hole origins or early universe structure. Its role is to expand observational access into regimes that were previously theoretical. What comes next is the systematic effort to interpret, test, and constrain what those observations imply. JWST's future contributions will focus on refinement rather than novelty. Early discoveries demonstrated that massive black holes exist earlier than expected. Follow-up work will determine how common such systems are, how their properties vary with environment, and how they correlate with host galaxies. Statistical clarity matters more than isolated examples. A small number of extreme cases can mislead if treated as representative. Spectroscopic analysis will be central. JWST's ability to resolve chemical composition, ionization states, and kinematic structure provides indirect constraints on black hole influence. By comparing galaxies with and without active nuclei across redshift ranges, researchers can infer how compact objects affect early evolution. This does not identify primordial black holes directly, but it narrows formation scenarios. Time allocation will increasingly favor population studies over deep single targets. Early campaigns prioritize detection. Later phases prioritize characterization. Understanding distributions matters more than confirming existence. This shift mirrors earlier phases of astronomy, where discovery preceded census. JWST will also contribute by identifying anomalies rather than confirming expectations. Systems that do not fit established models often provide the most leverage. Chemically primitive galaxies with unexpectedly massive black holes remain a priority because they strain stellar-only explanations. Additional examples will strengthen or weaken the case for alternative origins. Coordination with other observatories will become essential. JWST operates in infrared wavelengths. Its findings must be integrated with data from radio, X-ray, gravitational wave, and cosmic microwave background experiments. No single instrument can resolve the full picture. JWST's value lies in anchoring multi-messenger interpretation. Gravitational wave astronomy represents the most direct complement. As detector sensitivity improves, merger statistics will refine black hole population models. JWST provides environmental context for these mergers by characterizing host galaxies at high redshift. Correlating merger rates with galaxy properties will test formation pathways. Microlensing surveys will also advance independently of JWST. Space-based and ground-based programs will extend sensitivity to smaller masses and wider fields. JWST's contribution here is indirect, providing redshift distributions and background source catalogs that improve lensing interpretation. Theoretical development will proceed alongside observation. JWST has already forced revisions in formation efficiency, accretion modeling, and early galaxy evolution. Continued data will constrain parameter space rather than suggest new physics outright. Models that survive will do so through flexibility rather than assertion. Importantly, JWST will not resolve quantum gravity questions. Evaporation behavior and remnant scenarios remain outside its observational reach. Progress there will depend on theoretical work and indirect astrophysical constraints. JWST's influence is contextual rather than decisive in this domain. The pace of refinement will be gradual. JWST observations accumulate slowly by design. This limits overinterpretation but requires patience. Claims will evolve incrementally as sample sizes grow and uncertainties narrow. Public interpretation will likely lag behind scientific consensus. Terms like terrifying or unprecedented reflect communication choices rather than research direction. Internally, the field will remain cautious, emphasizing uncertainty and constraint rather than declaration. One of JWST's most important future roles will be negative definition. By ruling out certain environments, timelines, or efficiencies, it will reduce the range of plausible explanations. Narrowing possibility is often more valuable than expanding it. The endpoint of this process is not certainty, but resolution within bounds. Primordial black holes may remain possible but constrained, or they may fade as explanations converge elsewhere. Either outcome represents progress. JWST's contribution to black hole research therefore lies in discipline. It forces alignment between theory and observation across scales. It prevents reliance on untested assumptions by making early universe conditions observable. What comes next is not a single discovery, but a decade of synthesis. JWST will continue feeding data into a broader effort to understand how gravity shaped the earliest structures. Black holes are part of that story, whether or not they are primordial. In addition, JWST's extended mission will allow repeated observations of the same regions, enabling consistency checks that were not possible with earlier telescopes. Variability studies, improved redshift calibration, and deeper cumulative exposures will refine earlier interpretations. These long-term datasets are particularly important for distinguishing between transient phenomena and persistent structural features. JWST will also inform target selection for future observatories. Its results will guide where next-generation telescopes focus their limited time, ensuring that follow-up efforts test the most informative scenarios. In this way, JWST functions as both an observer and a coordinator. shaping the direction of cosmological investigation beyond its own operational lifetime. Beyond specific techniques, JWST will influence how questions are framed. Rather than asking whether a single explanation is correct, future research will increasingly ask which combinations of processes best reproduce observed trends. This shift reflects recognition that early universe phenomena rarely arise from isolated mechanisms. Black hole formation, galaxy assembly, and dark matter behavior are intertwined, and JWST data encourages integrated modeling. JWST will also sharpen the distinction between theoretical plausibility and observational relevance. Some scenarios may remain mathematically consistent, yet observationally unnecessary. Others may prove essential, even if initially counterintuitive. JWST helps sort these categories by providing empirical anchors. Another outcome will be refinement of uncertainty itself. Rather than shrinking uncertainty uniformly, JWST redistributes it. Some parameters become tightly constrained, while others are exposed as poorly understood. This redistribution is productive, directing attention to where new physics or improved modeling is most needed. Finally, JWST's ongoing contribution will be cultural within the scientific community. It reinforces a cautious approach to early claims and a willingness to revise narratives as data improves. This culture shapes not only black hole research, but cosmology more broadly. In that sense, the future is methodical rather than dramatic. JWST's legacy will be measured not by one unsettling implication, but by how thoroughly it reshaped the questions cosmology asks and the rigor with which it demands answers. Why this discovery changes how we think about the universe. The most consequential outcome of recent James Webb Space Telescope observations is not the identification of a single unexpected object, but a structural shift in how the early universe must be understood. JWST has shown that many foundational assumptions about timing, sequence, and efficiency in cosmic evolution require revision. The universe revealed by these observations operates within known physical laws, yet it organizes matter faster and more decisively than long-standing models anticipated. For decades, cosmology relied on a broadly sequential narrative. Small structures formed first, stars ignited gradually, chemical enrichment followed, and black holes emerged later as byproducts of stellar evolution. This framework was supported by observations of the nearby universe and by simulations constrained by limited early universe data. JWST has now disrupted this narrative by directly observing massive galaxies, compact objects, and energetic systems at epochs previously thought too early to support such complexity. These observations do not invalidate the standard cosmological model at large scales. Expansion history, background radiation, and overall matter distribution remain well described. What JWST challenges is the internal chronology of structure formation within that framework. The early universe appears capable of producing large, organized systems with minimal delay, suggesting that collapse and growth processes operate with greater efficiency under primordial conditions. One major implication concerns gravitational collapse. JWST data indicate that dense structures formed rapidly once threshold conditions were met. This suggests that early matter distributions, radiation fields, and cooling mechanisms allowed gravity to dominate sooner than expected. Rather than being gradually moderated by feedback, collapse appears to have proceeded decisively in some regions, producing compact objects and galaxies on compressed timescales. This efficiency has consequences for how causality is assigned. Previously, stars were assumed to be the primary agents that shaped early galaxies, with black holes emerging afterward. JWST reveals systems where this ordering does not apply. Black holes appear present before extensive stellar buildup, indicating that gravity itself may have been the organizing force, with stars following rather than leading. The implications extend beyond black holes. If matter can organize rapidly into deep potential wells, other structures may also form earlier or differently than expected. JWST encourages reconsideration of which processes are fundamental and which are contingent. Some phenomena previously treated as outcomes may instead be drivers under certain conditions. Another consequence involves chemical evolution. JWST has identified early systems with low metallicity yet high mass and compactness. This combination suggests that significant structure can form without prolonged stellar processing. Chemical enrichment, once thought to be a prerequisite for complexity, may instead be a parallel or subsequent process in some environments. This challenges intuition shaped by local observations. In the present universe, complexity correlates strongly with chemical maturity. JWST shows that this relationship does not universally apply. Early universe conditions differ sufficiently that analogies based on nearby galaxies can mislead when extrapolated backward. The discovery also reshapes the role of rarity. Many early JWST findings were initially described as exceptional. As samples expanded, patterns emerged. What once appeared anomalous began to look recurrent. This shift matters because cosmological models often treat rare outcomes as negligible. JWST demonstrates that outcomes previously considered unlikely occurred frequently enough to influence large-scale structure. Probability, therefore, must be reconsidered. The early universe explored a broader range of physically allowed outcomes than models assumed. JWST does not suggest that laws were violated, but that those laws permit faster and more extreme organization than previously appreciated. This expands the solution space of cosmological evolution. The telescope also alters how uncertainty is managed. Prior to JWST, gaps in observation allowed theoretical freedom. Many competing explanations could coexist without strong constraint. JWST narrows some of these gaps while exposing others. Certain mechanisms become unnecessary rather than impossible. Others remain viable but tightly bounded. The result is not closure, but refinement. This refinement affects dark matter discussions as well. JWST does not identify dark matter directly, but early structure formation places constraints on its behavior. Any dark component must be consistent with rapid early collapse without excessive disruption. This limits interaction strengths, thermal properties, and clustering behavior. JWST thereby informs dark matter theory indirectly by constraining what cannot occur. Another shift concerns methodological priorities. JWST demonstrates that confirmation-based observation is insufficient. The field must also investigate why the universe selected efficient pathways. Instead of asking how long processes take under idealized conditions, cosmology must explain why early conditions favored rapid outcomes. This reframing elevates initial conditions and environmental context as central explanatory factors. JWST also forces reconsideration of feedback assumptions. Many models rely on stellar feedback to regulate early growth. Observations of black holes without mature stellar populations suggest that regulation may have been weaker or delayed in some systems. This alters predictions for gas dynamics, star formation efficiency, and black hole growth during early epochs. The discovery further highlights the limits of simulation. Numerical models often impose resolution thresholds, simplified physics, or average feedback prescriptions. JWST reveals outcomes that simulations did not prioritize, not because they were forbidden, but because they were statistically de-emphasized. This encourages development of models that better capture extreme but permitted scenarios. There is also a philosophical shift. JWST undermines the notion that complexity requires long preparation. The early universe was not tentative. It assembled structure decisively once conditions allowed. This challenges narratives that portray cosmic history as a slow ascent from simplicity. Complexity appears to have been available early, not earned gradually. This realization does not imply danger or instability. The universe remains governed by the same constraints. What changes is perspective. JWST reveals that the universe does not optimize for human intuition. It explores what physics allows, not what appears orderly by narrative standards. Public framing often emphasizes fear or awe, but within science, the response is measured. The unsettling aspect lies in recognizing how much confidence was placed in assumptions now shown to be incomplete. JWST demonstrates that even well-supported timelines can be revised when new observational windows open. The telescope also influences future research strategy. Rather than searching for singular decisive evidence, the field must integrate multiple weak constraints across disciplines. Infrared astronomy, gravitational wave detection, particle physics, and theory must converge. JWST provides anchor points, but not final answers. Importantly, JWST reminds researchers of observational humility. Some questions may resist definitive resolution. Different histories can produce similar observables. JWST reveals outcomes without always revealing origins. This limits how conclusively models can be favored or rejected. The most profound change is conceptual. The universe revealed by JWST is efficient, flexible, and capable of early extremes. It does not wait to become structured. It acts quickly, within the allowances of physics, producing systems that persist for billions of years. This realization reshapes cosmology's narrative foundation. The early universe was not a fragile prelude. It was a decisive phase of organization. JWST forces recognition of that decisiveness and demands that models reflect it. The discovery changes how questions are asked. Instead of asking whether such systems should exist, cosmology must ask why they formed so readily. That shift marks a fundamental change in perspective. JWST has not revealed a hidden threat or a singular anomaly. It has revealed a universe that uses its physical laws more effectively than expected. That effectiveness, once recognized, alters the entire framework through which cosmic history is interpreted. This is why the discovery matters. It does not close the story. It changes its structure.